Good morning, everybody. We resume this fourth day session with historical talk. And so we are going to talk. Alberto Cogliati is talking about the history behind Gauss, Disquisitiones, circa, superficies, curvas. Detto in latino malissimo. The switch between English and Latin didn't work out. So please start.
Okay, so thank you very much for the invitation. I'm really glad to be here. We are taking a step back of about 200 years with respect to, I guess, the topics that you've been discussing over this day. So the idea is uh, to describe the scientific path that led Gauss to the drafting of his celebrated Disquisitiones Generales circa superficies curvas, in which, as you well know, Gauss laid the foundations of modern theory of surfaces. To do so, it is useful to have an idea of the state of the art concerning research on the theory of surfaces prior to Gauss. And therefore, the first part of this talk will attempt to outline this situation, essentially starting from the first half of the 18th century. Then, in more detail, I will try to explain how Gauss arrived at some of his most important results, and in particularly how he reached the proof of the so-called theorema egregium, the theorem according to which the Gaussian curvature is preserved under local isometry. His theory is purely local. There is no global consideration at all. And finally, I will try to describe how Gauss' work was received by his contemporaries up to about the middle of the 19th century. Let's begin with our protagonist, Carl Friedrich Gauss, and maybe it's useful to provide a few biographical coordinates of his scientific life. Gauss was born in Brunswick in 1777, and as we know, from a very early age, he displayed an exceptional talent for mathematics and study in general. A talent that opened to him the doors of the Collegium Carolino in Brunswick, which he was able to attend thanks to the financial support of the Duke of Brunswick, allowing him to access to higher education. In 1795, he moved to Göttingen, where his education developed almost entirely independently. In essence, Gauss was a self-taught scholar. His early research dealt with arithmetic and number theory, and it was precisely these first studies that led to the publication of his opus magnum, that is the Disquisitiones Arithmeticae. As you can see, his investigations on the theory of surfaces belong to a later, more mature phase of his scientific career. And the work that will concern us, the Disquisitiones Generales, was presented to the Academy of Sciences in Göttingen in 1827 and was published the next year in the proceedings of the same academy. In actual fact, as I will try to explain, this work is the result of a very long and gradual process of reflection that occupied Gauss for at least 2 decades. So here we can see the title page of the work, which was written in Latin. There are many translations in Italian, in English clearly. And as you can see, the subtitle explicitly states that the memoir was presented by Gauss to the Academy in October 1827. The work is universally and rightly regarded as the founding act of modern theory of surfaces. In it, Gauss introduces a series of technical tools that have since become classical. For example, the analytical representation of a surface in terms of a two-dimensional parameterization of points in space, the notion of Gauss map, and the concepts of the first and second fundamental forms. The Disquisitiones also marks the beginning of a new phase in the study of surfaces, one that focuses on the property of surfaces which are independent of the particular way in which the surface is embedded in ordinary space. Gauss didn't have any clear idea of a surface in terms of an abstract manifold. He always thought of a surface in terms of an embedded surface, but still he understood very clearly the opportunity to focus on intrinsic properties. To fully appreciate the innovation introduced by Gauss, it is useful to understand the state of the research at the time when Gauss began to engage with these questions. In fact, the Disquisitiones represents both the culmination of a centuries-old tradition of studies and a new starting point. So here you'll find a list of some steps towards the history of towards Gauss' work on surface theory. So just to give you an example, as late as 1715, Leibniz and Johann Bernoulli discussed the problem, what's a surface? What does it mean to represent a surface in analytical terms? And there is a letter from Johann Bernoulli to Leibniz in which he explained that according to him, a surface is simply described in terms of the relation among three variables. So you see, relatio, data, equazione, exprimetur per ordinata stress. A few years later, the very young Euler, he was 20 at that time, gives an analytic treatment of curves on a surface that realize the minimum distance between two given points. He didn't use the word geodesics because the word geodesics was limited to geodesics on the sphere and used the expression linee brevissime. After that, Euler, 4 decades later, introduced the notion of principal curvatures in an important research which he published in the Proceedings of the Berlin Academy. And also we mention another work by Euler on which I will say something a little bit later. And then we have what we can describe as the French school of differential geometry. That is a group of mathematicians which concentrated around the figure of Gaspard Monge. Intuitively, a surface in space is the outer part of a solid, as you can see, and that is the meaning of the Greek word epiphania. It's precisely this one. It's a word which Euclid also employed. And also we have the Latin calca superficies that reflects the concreteness of this intuition. As I was saying, a formal concept emerged only with the abstract definition of differential manifold in the first half of the last century. And before then, a surface embedded in Euclidean space was typically identified with the locus points satisfying a relation subject to a suitable regularity. Beginning with Euler, and even more so after Gauss, the practice became to view a surface as any two-dimensional parameterization of points in space. So let's have a look at Euler's work on geodesics on a surface. It was Johann Bernoulli who first understood the possibility of characterizing these type of curves through a remarkable geometrical condition, which is nowadays known as the Bernoulli's theorem. As you can see, this is an entirely extrinsic characterization of geodesics, that is one depending on the way in which the surface is embedded in space. Bernoulli didn't provide any proof of this theorem. It was Euler, the first one to give an analytical treatment of the problem. And I won't go into the detail, but here you find a letter from Euler to Johann Bernoulli, in which for the first time he wrote down the analytical condition. And as you can see, this is the analytical condition, which is quite obscure. Here you'll find an English translation, but okay, it's not difficult to understand that this is equivalent to the following condition, which we can clearly understand as the analytical content of the Bernoulli's geometrical condition. In a later work published in 1767, but already written in 1763, Euler specifically addressed the problem of curvature of a surface, motivated by the evident need to give it a unique characterization. Euler explains that, unlike the notion of curvature for plane or spatial curves, there was no adequate concept to mathematically describe the curvature of a surface. And the main result of the memoir to which we are referring is the existence of two mutually perpendicularly directions along which the normal sectional curvatures take on their maximum and minimum values. Clearly, I am using the vector notation, but it's a pure anachronism. Please be careful. Euler employed the expression principal directions, but in a completely different meaning. So I am, okay, I'm not philologically rigorous in that. Euler's proof is very, very simple, just pure computation. He starts by computing the sectional curvature of a section obtained by intersecting a given surface with a generic plane. And then he specified this plane in order for it to be normal to the surface, but so pure computation. Here is a picture as you can see, it's also a little bit difficult to understand the picture in Euler's article, and on the left there is a three-dimensional analog. As you can see, the very existence of these two principal curvature was regarded by Euler to be an explanation of the very concept of curvature of a surface. Indeed, he said, however complicated this judgment of surface curvature may appear at first, for each element it reduces to the knowledge of two radii of curvature, one greatest and one least. Maybe the most interesting work by Euler on surface is this one. It's less well known. De solidis quorum superficium in planum explicari licet. And this is particularly interesting because Euler was the first to systematically consider the problem of applicability, that is local isometry between a given surface and the plane. And so Euler wanted to determine all the surfaces which are locally isometric to the plane. And in order to do that, he introduced some significant innovation. For example, the idea that the surface can be described in terms of two parameters. This was a novelty, right? It may appear to us quite trivial and simple, but it was an important step forward. These coordinates are usually called Gaussian coordinates, but in actual fact, it was Euler who first introduced them. This is also another interesting point, is the fact that Euler was able to deduce analytical conditions guaranteeing, in actual fact, a necessary condition for a surface to be developable on a plane. And in doing that, as you can see, he found something which is equivalent to the coefficient of the first fundamental forms, because in Formula 4 there you can find the combinations of the coefficients of the first fundamental form. And so the requirement is that these coefficients coincides with the coefficients of the first fundamental form of the plane. Gaspar Monge get interested in Euler's work, and he was able to deduce a condition which looks to us much more familiar, because he was able to reformulate Euler's condition in terms of that equation. Please note that according to Monge, the surface is described in terms of the graph of a function of in two variables. This is yes, clearly this is equivalent to the requirement that Gauss curvature is equal to 0. But yes, there is no general definition of the notion of curvature. So finally, we come to our Disquisitiones. Here you find a list of what I believe are the main innovation introduced by him. That is a proper definition of regular surface. What is a regular surface? According to Gauss, it's a surface which at each point has a tangent plane. So there is some regularity condition in there. And then we also find the definition of the Gauss map by using various representations of a surface. There is the definition of Gauss curvature. I will talk about it a little bit later. And then the introduction of the coefficients of the first and the second fundamental form. And after that, a proof of the theorema egregium, and then an intrinsic treatment of geodesic line, and much more, the introduction of spatial coordinate systems, such as polar geodesic coordinates, and various theorem on angular defect or excess. As I was saying before, this work is the product of a very long process of reflection. Indeed, in January 1827, Gauss wrote to his friend Schumacher by referring to the drafting of the Disquisitiones. I find many difficulties in bringing it, that is the Disquisitiones, to its final form. But what one might call mere polishing is not what slows me down, setting aside the weakness of my Latin. Rather, it is the internal interweaving of truths in their combination. Such work succeeds only when the reader no longer perceives the enormous effort that went into it. So I think that this is an interesting statement because Gauss expressed the need to provide the text with a formulation which is completely different from the heuristic path that he had followed in the discovery process. We know very much about this discovery process. A 19th century historian of mathematics, Steckel, reconstructed the timeline of Gauss's advances. And this list is essentially based upon an analysis of unpublished material, manuscripts. Please note that is far from being certain. Some aspects of this reconstruction are, how can I say, speculative and conjectural. But more or less, we can say at some point between 1799 and 1813, Gauss had the idea of introducing his Gauss map. He defined his notion of curvature, and he identified his curvature in terms of the product of the two principal curvatures. In 1816, and this is certain, he had the idea that the curvature is invariant under isometries. Between 1823 and 1825, he deduced expression for the Gaussian curvature in special coordinates, such as conformal coordinates and polar geodesic coordinates. In 1825, he proved the theorem according to which the sum of the interior angles of an infinitesimal geodesic triangle is linked to the curvature, the integral curvature of the triangle, and finally arrived at the derivation of the curvature formula in arbitrary coordinates. Okay, so I won't give you the detail, but when I mentioned before that his discovery of the truth of the theorema egregium dates back to 1816, this is almost certain, I would say. This is a translation. So the most general solution for determining all shapes of a given curve can assume rest on the following fact, and which is a condition essentially coinciding with the equality of curvature. But still, there is an important annotation because he said this beautiful theorem, that is theorem egregium, is certainly correct, but it does not suffice to solve the problem. That is, the quality of Gaussian curvatures is not sufficient to guarantee local isometry. But Gauss never discussed this point. The first one to discuss it was Ferdinand Minding much later. There is a curiosity I'd like to tell you. That is, we cannot exclude the hypothesis that Gauss had the idea of introducing his notion of Gauss map and maybe of his curvature from the reading of a memoir written by a mathematician whose name is Olinde Rodriguez, which in actual fact in 1815 considered that integral, which we can interpret as the surface integral of the Gaussian curvature. And he linked this integral with the geometrical meaning of the Gauss map. But there is no, we are not certain. The introduction of this notion on Gauss' part might have been completely independent. Gauss' proof of the theorema egregium in the Disquisitiones is purely analytic. Everything turns on expressing the Gaussian curvature purely in terms of the fundamental form and its derivatives, clearly. And so the idea is that since the curvature depends only on these coefficients and their derivative, and two locally isometric surfaces can be parametrized so that these functions agree, then the curvature must be invariant under isometries. This is proof. Okay, this is the quotation and the statement of the theorem. If a curved surface is developed onto any other surface, curved of plane, the measure of curvature, that is the Gaussian curvature, at each point remains invariant. Clearly, the demonstration that Gauss provided in his Disquisitiones doesn't tell us anything about how he discovered it, because it is highly unlikely that he arrived at the theorem by the analytical route, because it's really a little bit complicated to deduce this formula. So that's not his heuristic path. But we know a lot of things about the discovery process. In particular, in 1825, 2 years before the final drafting of the Disquisitiones, Gauss wrote an essay in German. This is the title, Neue allgemeinen Untersuchungen über die Krummenflächen, which he never published. This essay was published only posthumously in 1900 in the 8th volume of Gauss' Werke. And this is a very interesting reading because in it we can find the original proof of Gauss' theorema egregium. In the Neue Untersuchungen, Gauss represents surfaces as the zero of a set of zero set of a function. He then introduced the Gauss map. He introduced the notion of Gauss curvature. And what's the idea? The idea is a purely geometrical definition. You consider on your surface a small area around a given point, and then you consider the image of this area on the unit sphere. You compute the area of these two regions, and the curvature is simply the limit of the ratio of these two areas. The image of the area on the unit sphere is an area which has a sign depending on the fact that the Gauss map preserves or not the orientation of your path. Underlying Gauss proof is the following result, which is an embryonic form of the Gauss-Bonnet theorem. So in his original proof, Gauss first proved the so-called Gauss-Bonnet theorem, and from that he deduced the theorema egregium. So here is the formulation of this theorem in die neuen Untersuchungen. The sum of the interior angles of a geodesic triangle, delta, equals pi, plus the oriented area of its spherical image. This theorem clearly admits of a generalization in terms of geodesic polygons. How Gauss proved this result? This is a very complicated proof which rests on intricate consideration of spherical geometry. This is really complicated, and the complexity of this proof is probably the reason why Gauss was unsatisfied with this logical structure. So when 2 years later he discovered a purely analytical proof of his theorema egregium, he was very happy because he found in that proof a truly rigorous treatment. So let us see how from this result, that is the Gauss-Bonnet theorem, one can deduce the theorema egregium. So you find it there a translation of Gauss words. So he said, if a curved surface can be developed onto another surface, then all curves on the first retain their length after development. That is the very definition of isometry. Angles between intersecting curves are likewise preserved. So isometry preserves both lengths and angles. Hence, geodesics remain geodesics. Therefore, if to every geodesic polygon on the first surface there corresponds a spherical image on the unit sphere of area A, and to the developed polygon a spherical image of area A prime, then A is equal to A primed. That is, given two locally isometric surfaces, S and S prime, we consider a geodesic polygon Pn on S, and to this geodesic polygon, it corresponds on the surface S primed another polygon P prime of N. And from the previous lemma, we find that not only the area of the polygons is the same, but also the area of their image upon the unit sphere. This is a consequence of the Gauss-Bonnet theorem, because the area of this image can be expressed purely in terms of the angle of these polygons. And that is, since isometries preserve angles, it follows that conditions. Although the proof of the Gauss-Bonnet theorem assumes geodesic boundaries, it clearly, said Gauss, holds in general because since the statement is independent of the number of sides, any polygon whose sides are not geodesics can be approximated by a polygon with infinitely many sides of minimal length. That is, any closed path can be approximated by a suitable geodesic polygon. And so we finally have the proof. Every figure also preserves its area under development. So we have to consider 4 areas. So he said, consider 4 figures. 1, an arbitrary figure on the first surface. 2, its spherical image on the auxiliary sphere. 3, the developed figure on the second surface. 4, the spherical image of 3. For infinitesimal figures, the ratio 2/1 yields the curvature at the point. You have clearly, this is not very rigorous, but okay, that's highly intuitive. Similarly, 4/3 gives the curvature on the second surface. Hence, under development, the measure of curvature is invariant. We have to keep in mind the fact that this demonstration was not published by Gauss. He limited himself to publishing the proof of the Disquisitiones. And so it is interesting to get an idea of how his Disquisitiones was received. In actual fact, one of the first response to Gauss' Disquisitiones was a paper by Jacobi dating back to 1837. You can see Demonstratio et amplificatio nova theorematis Gaussiani de curvatura integral. That is a proof and an extension, a new extension of the theorem of Gauss. What's interesting in Jacobi's work is the fact that he was not satisfied with Gauss' treatment of curvature and of his theorema egregium, because he thought that the geometrical significance of the theorem was somehow hidden by the analytical apparatus. And so he provided a kind of generalization of Gauss-Bonnet theorem by proving this result, that is a sort of Gauss-Bonnet theorem which is independent from the existence of a surface. You simply consider 3 curves in space such that these 3 curves build up a triangle you consider the normals to these curves, and you suppose that at the vertex of this triangle, these normals have the same direction. And then you consider what is called the indicatrix, that is the spherical image of these 3 curves, by mapping a point on the curves to the point which corresponds on the sphere, which corresponds to the normal to this curve. And Jacobi found a result which is somehow a a sort of generalization of Gauss theorem. His proof is purely geometrical, and it was very very glad about this discovery because he regarded this result, as you can see, as the verum fontem theorematis Gaussiani. That is, this is the true source of the theorem of Gauss. So Jacobi had found a geometrical proof of the Gauss-Bonnet theorem, which he regarded much better than the one provided by Gauss, because in the Disquisitiones we find a purely analytical deduction of the theorem of the Gauss-Bonnet theorem, which is based upon the use of geodesic polar coordinates. So also in this case, Gauss had preferred an analytical treatment, which was not very satisfactory, according to Jacobi. Another interesting paper concerning the reception of Gauss' work is this paper by Ferdinand Minding. This is important also because Minding was the first one to provide both necessary and sufficient condition guaranteeing the fact that there exists a local isometry between two surfaces. And what is interesting is the following fact, that Minding clearly didn't know Gauss' original proof of the Theorema Egregio. And so what he did is simply he rediscovered Gauss' original proof by regarding it much better than the one that Gauss had provided in his Disquisitiones. So maybe we don't have time to go into the detail, but this is precisely the proof that we have seen before. Other attempts at finding alternative proofs of the Theorema Egregium were pursued in France at that time, and this is an alternative proof proposed by Joseph Bertrand in 1848. This is based on a very simple and geometrical idea. The idea is to compute the length of a geodesic circle. By a geodesic circle, I mean the set of points whose distance from a given point is constant when the distance is measured along geodesic curves. And since Bertrand proved up to terms of order r to the power of 4, this length depends only on the geodesic radius r and the Gaussian curvature, it follows that Gaussian curvature itself is invariant under isometries. If r is the geodesic radius and R1, R2 are the principal radii of curvature at the center, then we have this expression. And as you can see in the quotation, this provides une nouvelle démonstration du théorème de Gauss. There are many alternatives demonstration of the theorem egregium. I counted, I guess, 12 since Gauss, the publication of Gauss Disquisitiones. So some final remarks. The first proof of the theorema egregium, which Gauss found in 1825, is distinctly geometrical and far more intuitive than the one Gauss published in his Disquisitiones. He later preferred a purely analytical approach, probably considering it more rigorous than the geometrical argument. The work of Gauss was immediately recognized as a milestone in the theory of surfaces, opening a new perspective focused on intrinsic properties. But Gauss' analytical methods were regarded by some, Jacobi, Minding, and others, as inappropriate or detached from geometrical intuition. And indeed, for nearly 30 years after the publication of the Disquisitiones, many mathematicians produced alternative proofs of the theorema egregium, aiming to restore a closer connection to geometrical reasoning. Sometimes they were not discovering new proofs, they were simply discovering proofs that Gauss had disregarded. This opposition between geometrical methods and analytical methods is an important factor of the development of differential geometry in the 19th century. And indeed, the debate on the legitimacy of using analytical tools in differential geometry and in surface theory did not end with Gauss. Essentially, the legitimacy of using analytical tools was definitely recognized only much later, I would say only after the publication of Riemann's Habilitationsvortrag, in which he provided a brand new foundation of differential geometry and differential manifolds. So that's essentially what I wanted to tell you, and many thanks for your attention.
Thank you for your very nice presentation. Are there any questions?
The idea that the surface may not strictly be in R3, but also in a higher dimension, in which case the differential definition makes sense while the other one doesn't, was not there, right?
No, at that time it was not there. In actual fact, that's another very interesting story, because, for example, the idea that Gauss theory could be generalized to higher dimension came only after the publication of Riemann's Habilitationsvortrag. And for example, when you consider surfaces in higher dimension, that is hypersurfaces, many strange things happen. So for example, as you know much better than me, there are rigidity phenomena, which were soon discovered, but they were, for example, regarded to be too much strange, such as to suggest that this extension is not logically sound. So, for example, when in 1870s, mathematicians discovered that in almost cases, hypersurface in dimension greater than 3 are rigid, that is the first fundamental form fully determine the hypersurface in space. This was regarded as something which cannot be possible. And so this was regarded as a logical inconsistency. So as a logical inconsistency coming from the fact that the extension to higher dimension is meaningless. But at this time, no higher dimensional spaces were considered.
So in Mending's paper, does he really show that the condition of equal curvature is necessary and sufficient? I mean, in higher dimensions, that's attributed to Riemann. But if you look at Riemann's proof, he essentially only proves that it's necessary, and then he sort of says, well, by sort of tracing back the steps, we see that it's also sufficient, which is, I mean, not so obvious.
No, there mathematicians at that time had not a very clear idea that a condition can be necessary but not sufficient. I'd say, for example, Bonnet had a completely wrong proof of the fact that the equality of Gaussian curvature is sufficient to guarantee local isometry. Mendings discussed in particular the case of constant curvature surface by providing a very detailed proof. And he also had conditions for the general case, but it is clear that he knew that the quality of the curvature is not sufficient in general. Some passages by Riemann are really quite obscured. Indeed, when you read Riemann, there are some passages in his Habilitationsvortrag in which he seems to say that even in 2 dimensions, the equality of surfaces, the equality of the Gaussian curvature is sufficient, which is wrong. But judging that paper is a little very difficult because, as you probably know, there is no formula in there. It's purely words, very clever words, but I mean purely words. And the case which I was mentioning before, that is the case of the rigidity of hypersurfaces, was discussed by an almost unknown mathematician whose name is Richard Bates. Indeed, the theorem of rigidity of hypersurfaces, it is sometimes called Bates' theorem. But we are, I guess, in 1876.
Historical question. So what is the role of Bonnet in Gauss-Bonnet? Because what you described is, okay, maybe because it was unpublished, because what you described, I mean, okay, one can argue about sort of discussing continuous geodesic curvature by where you can really break it into polygons, but otherwise, I mean, it really seems to be...
The contribution of Bonnet is what happens when curves are not geodesic. And so you have to consider the geodesic curvature. And so that's his contribution. So, I mean...
I also have a question. At some point in your presentation, it appears something in a kind of integral form by
Rodriguez.
What was he able to do with such formulation?
Not much.
I expected not that much.
Actually, for example, I don't remember exactly, but at a certain point, he was interested in computing the total curvature of a torus, and but he made some mistakes with the sign of the curvature, so he find a wrong result. Essentially, Rodriguez's work was linked with the Monge tradition, that is, which was based upon this idea. A surface can be studied by studying the property of special curves on the surface. So, for example, this integral comes from his study of the lines of curvature on a surface, but he was not able to do very much with this result. Actually, it was up to Gauss to find a fully systematic and systematic formulation. And so,
Okay, thank you. Sorry, Antonio.
Thank you very much. Just a curiosity. So the beautiful story that you've told us, I mean, is it written somewhere that we can use it to quote? Because I mean, maybe disclosure, right? So some of us knew a little bit of the story you told. And the reference is the second chapter of Spivak's book. But
yes,
of course, you gave us a beautiful perspective, and it would be, I think, very nice if we could share it with.
Okay, so the main source, okay, it's the 8th volume of Gauss Werke. There is an article written in German by Paul Stekel, Gauss als Geometer. And essentially, these results, these historiographic results, were at the basis of a very nice paper by Dombrowski. I'm Dombrowski. I'm not sure. Written in asterisk. I would say in about 1970, but I can give you a more precise reference. I have to check it. And on the reception of Gauss theorema egregium, okay, it's not very polite, but I wrote a book on the history of differential geometry. It's in Italian, which is Ars. This is the title, Ars Inveniendi. So it's Pisa University Press, 2000 and maybe. Okay. But I can give you a more precise reference to this.
Okay. If there are no other questions, we thank again the speaker. Okay, we continue. It's my pleasure to introduce Antonio Simona. He's going to talk about morphing of thin structure 200 years after Gauss, but also 100 years after Timoshenko.
Thank you. So this is not really improvised, but it was not planned. I mean, we were not planning that I, as an organizer, give a talk. The reason is because one of the speakers could not make it on Monday, and then the talk that was thought for this spot was Eran Sharon's talk, and we moved it to Monday. And so I decided to fill in a little bit because I was stunned by the quality of the talks that we have had up to now. So we are recording as much as we can, and so I wanted to maybe leave a little bit of a fil rouge behind some of the things we have seen up to now, and that we're going to see in the next 2 days. Also, okay, so I've disclosed why we knew about the 200, the secret anniversary. So, we're very proud of having spotted this opportunity for the 200 years of one of the, traceable places where to find the Gauss theorem egregium. And I wanted to say that with Eran Sharon, I mean, Eran is somehow the rediscoverer of, okay, let me put it this way. Eran is the discoverer of the Theorema Egregium of Gauss as a tool to shape things. So you have seen this. I will use this later on in the talk. You've seen this in the talk by Marino Arroyo. And so the idea is that you use you control the metric of something, so you stretch and deform something to shape it in space. Okay, and as strange as it may sound to mathematicians, this is a very non-intuitive idea, and the history of this idea is very short. I mean, maybe it's the 20th birthday, probably, of this idea, and so I wanted to talk a little bit about that. So there will be, so we've seen in the previous talk, analytical versus geometry versus analytical expression. So the thing that we'll add into this is the physicality of the objects, of these surfaces, and the mechanics. So there's elasticity as well. And okay, so okay, so let me start by acknowledging a little bit. Okay, I already told you that I owe a lot to Eran, Sharon, and this is a project that we are pursuing together. This celebrating the 100 and 200 simultaneous anniversary of the two most widespread tools to morph thin structures in contemporary, especially, for example, in robotics research. And so I also quoted Marino, who has been my companion for many years, and Luciano Teresi, who's going to speak later on, and I will say something joint with him, and Francois Luge as well. Okay, so here are the two anniversaries. Okay, we have already seen the portrait of Gauss, and so the idea of Gauss is so the idea of using a Gauss theorem is to actively control the metric so that you can control the Gaussian curvature, and so the way things shape in space. And in particular, the important thing is the fact that you generate shape changes by lateral modulations of the metric. So you have something, you change distances laterally in a thin sheet, and you accomplish shape changes. So you have seen Marino Arroyo's talk about this stuff that I'm holding in my hands. So this was something that made us very proud. So we said, Euglena, which is a 50 micron brainless unicellular organism, knows Gauss theoremic ratio. Okay, so I mean, a lot of people, you've seen how the acceptance somehow was this beautiful history of the acceptance, and Euglena does it effortlessly, even without brain. And so we were very proud. So this is a physical reconstruction of the mechanism, and so you have to twist it a bit, and then you turn it, and blah blah. So this is what Euglena does. Okay, and as you see, there is a modulation of a shearing deformation along this direction. Okay, okay, so we'll see this more in a second. I have also a portable version of this. This is difficult to. I have a portable version of this, and this is a portable version of something Alison Martin showed us. So these are. It's a similar concept, and I will show you larger pictures later on, in which, again, it's a modulation now of easier things to accomplish. These are shears or sliding, so you need something that can slide next to the other. The beauty of it is that the stroke is unlimited. So if you had an infinite strip, you could produce the change from an infinite cylinder to an infinite flat disk, and without any restriction. While this mechanism here is a bit similar. It's based on the stretching of a pantographic unit. And so this mechanism is very beautiful, but it locks. So it has the stroke, this is what engineers call this, is limited. It has two upper bounds. You can not do anything more than this, not anything more than that. And okay, it's a beautiful thing. And it's also something that immediately shows that mechanics, at some point, eventually, mechanics will play a role. I use it in a similar way as Alison uses it. I tease my student and I say, well, okay, look at this. And now compute the height at which the thing will go, right? And conceptually, it's a trivial thing. It's a conservation of energy argument. but it rests on the fact that you have to estimate the elastic energy that you have stored in the system when you release it. And this will give you the gain in potential energy from a zero kinetic energy to a zero kinetic energy state. And as you will see, it's an interesting exercise. But definitely, it's in looking at this problem, there is something that is to do with geometry. So the connection between the shape of these helices and the shape of the surface, and the mechanics. The mechanics is there, okay? And so this is another theme that is very dear to in the conversation between me and Eran. I come from engineering. I work with elasticity, finite elements, and Eran has this beautiful geometric view where we always talk about the interface between geometry and mechanics, where geometry, at which point geometry, so where does geometry reign and when is mechanics important? This other example would have been the topic of Manu Prakash's talk on Monday that we couldn't have it, but again, you see a similar thing. So it's a very interesting phenomenon. There is another unicellular organism that uses this dramatic shape change for two things. It's a predator, so it uses this protrusion in many directions to scan space. And then if it finds a prey, I mean, the beauty of unicellular organisms is that the mechanisms are very elementary, so you can think of physical. So I mean, there's no cognition, there is mood. I mean, these organisms are very moody. I mean, you cannot ask them to do what you want, but there's no cognition and there's no sight. So, for example, they can eat only when they strike a prey, and sometimes we see them hunting, and the prey is here, and you say, "Come on, go there," but she doesn't see it until it hits it. Okay. And so these are very interesting things, and you see here maybe the basic idea. So modulation, lateral modulation of the metric. Now, the other hero is a guy called Stefan Timoshenko, and in 1925, he published a paper with the analysis of a bimetallic strip. So this is a thin rod, so it's important for what I'm going to say later on. It's a thin rod, and there is the analysis of the fact that if you have two metals that shrink in a different way, so there is a mismatch strain due to different thermal dilation, then the thing will bend. And you can use this for many things, in particular thermostats. So we are not in the UK, but in the UK, I could have done an experiment of using a kettle, something to boil water. You would push a button, and then you would hear the water boiling, and then cluck. Okay, the cluck is the thermostat that switches from one. So it does this. It bends in an unstable way, and it breaks the circuit, and the thing switches off. This is 1925, but okay. I mean, this is a very popular thing. You can see it in nature. So this is the on of a seed. The seed is here, and all this part is passive, and it's a hygromorphic bilayer. So one part absorbs humidity, one doesn't, or they do it in a differential way. There is differential swelling, and this causes a change of shape that is used by the seed to bury itself. Okay, and so this happens over and over and over again, and it's something that is, caused a lot of attention. So this is the paper. The basic formula is that with elasticity in a rod, you can relate, you can find the radius of curvature, the curvature of this object through a simple formula. Let me see what I have here. Right, and this is very widely used. I'm showing you a concept that maybe comes from architecture. So there are the attempts of making self-morphing things using environmental stimuli, like changes of humidity, of temperature, of light, of things like that. And this is an idea for a kinetic facade that could open and close depending on environmental condition. And we have heard mention to this material, which is something that is dear to my heart, liquid crystal elastomers. These are materials which contain there is order at the microscopic level. And if you disrupt this order, you can deform the material. So you can think of it as if you had some aligned chains, and if the order is disrupted and the chain change orientation, one relative to the other, you will see a contraction. Okay? And so this can be done because by heating up this material locally, you can change the state of order locally. And there's also a variant in which you can put some molecules that are sensitive to light. You shine light, these molecules absorb a photon, they distort, and this will change the shape of the thing. Okay? And so here you see an example of, okay, it's a pillar if you want. It's an artificial cilium. And here you see it from the bottom. So here I think that Danxing Liu spoke about this the first day. By heating one side, you can cause shrinking only on one side, and the thing will bend. Okay, so this is the idea, right? So this is the side that has been heated from below. The material contracts here, and the thing bends in this direction. Okay, so never mind, we can go. And now there are interesting things that can be done with these materials. And so this will come later, but I will use it for the demo, for the idea. So it happens that, yeah, maybe let me go back to the last slide here. So the last slide, so this one you saw the fact that after a while the thing, becomes straight again. Okay, so these deformations rely on the fact that there is a gradient of the spontaneous state of the material, of the target state, the target metric, we would say. So the state in which the material likes to be. Okay. And so if you heat it heterogeneously, this state will be different from one region to the other, and you get deformation. This is the basic idea. Now, you can do this statically or dynamically. And the dynamic part is also very interesting. So you see that here you cannot maintain this bent state forever, because as you keep heating, as you keep providing current, the whole thing will become hot, too hot. Everything will transform and will become shortened, and you get back to a straight thing. Okay, so time is an important variable. This is why I was showing this. And time is an important variable because you can do dynamic effects. Okay, and this is the purpose of this. So imagine that, okay, I'm trying to describe this, so let me put it here. Okay, so imagine that now I have this rod that is made of this material that is light sensitive, for example. And for some reason, this material is bent upwards. Okay, I start from this configuration, and then I shine light coming from there. So it will be a side that is lit, the bottom one, and a side that is in the shadow, the top one. And if I disorder this part will shrink. The thing will bend will bend in the bottom, and the thing will bend towards the light. And then at some point, the role of being lit and being shadowed reverses, and the part that will be lit is this one. So if there is inertia in the system, this will start getting light, and I will go up. And then you can hope to engender emotion. Okay? And actually, this is one of the reasons why this material is so studied, because it's exactly like that. So you can, and the crucial thing is that you need to inject enough energy in the system so that the oscillations that cause dissipation are constantly fed by energy. So light has to be sufficient to sustain the motion. And so if the light is not strong enough, these oscillations will decay. If the light is strong enough, these oscillations will persist. Okay, I don't know whether you have recognized this. This is an instability, not of the kind of the static kind, but it's an instability towards an oscillatory state. So it's a Hopf type instability. And it's a very interesting strategy to harness energy from the environment and transform it into motion. Okay, so there are many applications of this idea. One could be, by the way, this is work done by a student of mine, Reza Nuruzi Kuriani. And yeah, so you can use this idea to pump. I can pump fluid upwards by shining light. And you can use this idea to produce artificial swimmers powered by light. So you can feed an object with photons, and this object will move in a fluid. And here there are two colors. I mean, this is technical, but I will not discuss this, why we're using two colors. But anyway, this is the basic idea is that you are causing this motion. Yes. Well, so there are two. So there are okay. There's a wave. Okay, there's a wave that propagates from here to there, and this wave is generating vortices that have been shed here and push the fluid up. Is that? Yeah. And so, I mean, this is, I mean, thank you for the question. I mean, I'm trying to go at a level that is not as detailed. We could ask the same question here. So why is this moving? Okay, because what you're seeing is a reciprocal motion. Okay, and so you're seeing something that is executing a very stupid breaststroke. Okay, so when you do breaststroke, when you want to power yourself, you want to maximize the resistance of the water because you want to push and you want to feel a lot of resistance. But then if you recover the shape to do the next stroke, what you do is you change shape so that the resistance is minimized. Okay? And so this is an asymmetry, while the stroke that we are seeing is reversible somehow. So we are doing the same thing on the two directions. So in this case, propulsion comes from the rate. Okay, so we are closing fast and opening slowly. So this is why the two colors of light. And okay, so the secret for this is inertia. Okay? So you're exploiting the fact that the inertial forces that you have to subject water to are very high if you move fast and can be lower if you move slowly. Okay, and this mechanism breaks down at a certain scale because fluid dynamics is not invariant with scale. And if you go at very small scale, so at the scale of the organisms that we were studying, so the micro scale, this will not work. Okay, but this is a very long story. I mean, it's a technical, but it's a very beautiful one. Okay, so let me skip this. I mean, this is so okay. Let me skip because otherwise it's too long. At some point, so we are saying that the materials want to do something. So there is this idea that Eran Sharon was alluding to on Monday, that there is a target state of the material, so a target metric. And the only thing I wanted to remind you is that when you go from rods, which are one-dimensional objects, where the strains are function of just one variable, and then you go to plates, where there are two dimensions, or if you go even to 3D, and then there is an issue that will start killing you, which is the issue of kinematic compatibility. So strains have to be the gradient of something, and in 1D, being the gradient of something is easy. I mean, fundamental theorem of calculus, you just find the primitive, and everything integrable, can be thought of as a derivative. But this is not true in higher dimension. In 2 dimensions, it's not true, and that's what we're going to see about Gauss. I mean, the compatibility between the metric and the curvature is a requirement of compatibility between the stretching behavior and the bending behavior, first and second fundamental. You cannot assign them freely. And if you do it in 3D, it's even worse. Okay, and so Luciano Teresi will talk about this issue a lot later on today. And this is another preview. So in this, there's a way of playing Timoshenko against Gauss in a sense. So this is a bilayer in which you're using the Timoshenko idea. So maybe you can see that this is a bilayer. There are two things, one next to the other, and they want to stretch in different directions. And this causes the thing to deform. Okay? And now there's something that comes into play, which is the width of the strip. Okay? The Timoshenko idea was for a very small, for something that has a very small width. And here you see a beautiful thing. And okay, let me just comment on the fact that this is elasticity. Okay, so this is 3-dimensional elasticity of an object that has aspect ratio that is special. Okay, Now you solve the problem, and these things comes at you. So here you see the behavior of the midline. And the midline is shown here. Now, if you look at this picture from the right angle, so if you look at it from here, you have the opportunity to see this is actually a cylinder. And that the midline is doing something which is like a circular helix. And this is what these pictures show you. This is a cylinder that you look from the axis, and this is the helix. And then as you move far away, you get something that becomes a straight line. And it's very straight, very straight. I think this is, the three-dimensional object knows nothing about this. The poor midline doesn't know to be a midline, except that it's in the middle, and it's doing all this. And so I think this is beautiful, right? And there must be reasons behind that. And so I think, if I understand correctly, we'll hear a bit more about this on Friday. Sharon has already talked about this on Monday. He showed us an example of this, and you will see work by Maria Giovanna Mora on Friday explaining this beautiful phenomenon. Okay, now let me go back to this guy a little bit. So this guy is, so this you already saw in Marino Arroyo's talk, so let me go fast. This guy has two behaviors. One is he uses flagella to move, to swim. And here you see our reconstruction. And then it has this other whole body behavior. Okay? It's a very interesting system because, again, no brain, no nothing, but this is a unicellular organism that can feel confinement. So it can feel that it's confined in a tube, in a capillary. If the capillary is tapered, it can feel that the tapering is more and more severe and change behavior. Okay, all this without brain. Okay, so there's sensing, there's decision making, a lot of things that can be studied, again, without cognition, conscience, and ethics. Okay. Now, what is beautiful about this is that the mechanism of the flagellum, the beating of the flagellum, and of the body is the same. It's all based on Gauss, and it's all based on the sliding of strips. So in the flagellum, this is a fact that is known through cryo-electron microscopy. We have heard about cryo-electron microscopy in, I think, in Carola Schoenlieb's talk, as a technique to, you want to reconstruct the molecular structure. So in that picture with all the colors, you see how this works in nature. So there are rods that are microtubules, and there are some molecules that change shape, and they can attach and they're anchored at one end, they can attach and detach on the other end, and they change shape. So when they attach and change shape, they kick the neighboring filament. And by the kicking, they introduce this relative motion. And so that system is this one, except that there are 9. Here I have maybe 20 stripes, but there are exactly 9 rods, and the beating of the flagellum is this one. Okay. The body should work in the same way, and so here you don't see. Okay, you don't see the flagellum. Okay, no, maybe. The body instead has this other behavior that we're discussing that is really based on Gauss theorem. And so there is an interesting in understanding that. This you saw in Marino Arroyo's talk. So this is the basic idea, right? One strip is pushed against the other. This causes shear. If you modulate that, you get Gaussian curvature. Now, okay. Geometry versus elasticity. So this is very beautiful, but I will return to this in a second. So let me go to this one because it's easier to analyze. I think. No. Geometry elasticity comes here already because this is a feature. So if you do it naively, this will not work. And the naivety comes from this. So if your strips do not allow the thing to bend in the plane, this is geodesic curvature. So if the stiffness of your constitutive rods is such that the the stiffness against geodesic curvature is high, this will not work. Okay? And it's interesting. I mean, I can show you papers of colleagues that have tried to reproduce our work and have they couldn't do it because they had not understood this fact. But this is the first reminder that elasticity is important, because in extreme regimes, like if there is a certain bending modulus that it's infinity, then you cannot explore those shapes. So while all this catalog of shapes that you're seeing here is geometrically attainable with a suitable change of metric, so a suitable sliding pattern, well, the rods will have to bend. Okay? And when I do this, I have to bend it, so I'm applying some forces. And okay, so I had a straight rod that has become a non-straight rod. Okay, so I'm storing energy into the system. In this case and in this case, it's the same. Okay, and if the stiffness in a certain direction is infinite, that direction will not be accessible to the system. Okay, so elasticity brings bounds to what is geometrically possible. Okay. And so when you study this system, which is a bit easier because it's made with this basic mechanism that, actually, it's the story about the success, the fortune of something is very interesting. Similar to the story we heard in the last hour about the reception of the idea. What is the best way of proving Gauss theorem egregium, etc. So there is a fact that this mechanism does not exist. Okay, so we managed to patent this. There is no engineering device that uses this thing, while this is prevalent. So there are something called pneumatic artificial muscles, where this system is used by putting a balloon inside, and the idea of this to make an artificial muscle, so something that contracts, thanks to the fact that the balloon inside expands. So this is a device that transduces lateral expansion into contraction. And so this is something that can be used to make pneumatic artificial muscles. And it's used this way. So this is a very well-studied system. And it's an interesting opportunity to somehow use this view that geometry and mechanics are two things. So we have studied this by deconstructing the two steps. So what about the behavior of this guy is purely geometric, and what about the behavior of this guy involves elasticity? So the end effect is to answer Allison's question and Allison's experiment about how my version of Allison's question, which is how high this will jump, right? So I want to estimate the stored energy. But in analyzing this system, there are two moments. One that is purely geometric, and it's the correlations between the beautiful color patterns, I don't know whether you can see them, okay, and the shape that you see. Okay? And this is pure geometry. And then the elasticity part. So this is what I call a destructured approach. Like you look at the two ingredients separately. And okay, so for example, the beauty of these things is that Gauss formula for the relationship between Gaussian curvature and first fundamental form and its derivatives becomes explicit. So you've seen maybe on Monday the equation for this guy. So it's a one-line thing. And the equation for this guy is very simple. Here it's written in terms of the angle of the threads. Okay? And this is telling you that basically, if you want Gaussian curvature, you need that this angle, so theta double VV is the derivative of the angle along the vertical direction. Okay? So it's telling you that if you want Gaussian curvature, you need these angles to change. Okay, sort of obvious, right? But it tells you quantitatively. And so, for example, there's a second derivative of something. So if okay, the something is constant, even its first derivative is constant, and so you get cylinders. So if I cut this, so this object is deforming in the way it's deforming because at the ends, it has been cut with a thermal thing that has fused the ends of the rods. So at the ends, you see that the thing cannot move, cannot expand laterally, right? And if I cut it, this will deform into a cylinder. Now, if I have something linear, then I get a cone. And if I want to get a bulge, which is the one that it's interesting also for biology because our thing was creating a bulge, you need at least, you know, a more complicated variation along the structure. This is pure geometry. So there's nothing but geometry in this, and it will be true no matter what you do for the you know, elasticity of the rods. Now, there is a way of constructing an elastic theory for this guy. Again, it's something that Marino Arroyo spoke about on Monday. The key thing is that whether I can recover all the quantities that are important for the elasticity of this object from the geometry. And the rods are curves on the surface. And so the tangent vector, I can read it from the geometry and from the shape of the curve. And now there's a key thing that is maybe more visible here. Because of the way these things are connected, basically one of the direction of the rods, if you want the long direction of a cross section, imagine a rectangular cross section. Okay, so I'm zooming it. And the cross section has two vectors, one which is a long vector and one which is a short vector. The short vector is always the normal to this surface because of the way these things are joined, right? So I have things like that, and so the short vector will always be the normal. So tangent, one vector. A vector of the cross section, the normal to the surface. The third vector of an orthogonal frame is given to you. So the geometry tells you everything about the way the cross section, the rod and the cross section sits in space. You can compute its energy. Okay, and so just from looking at the geometry, you can write down the energy of this as an assembly of elastic rods. Okay. So this, Marino said this very right, and interesting. So I don't know why, and so you can compute the stress-strain curve. I mean, this is, I don't know what happened, so it has been rotated. In principle, this would be the vertical axis, this is the horizontal axis. Okay, so think of it like that. Okay, so this is like an S-shaped curve. Okay, so blah, blah. And so this is the elasticity. So now you know about the elasticity, and now looking at this, there's a number of things you can observe. One is the secret. This guy maybe costs, I don't know. I mean, the cost of making this in a big industrial process is like 1 cent. And you buy it at €5 as a stress relief device for cats. And the secret of this guy is that there's a plateau in the force displacement response. Okay, so you compress and the force goes up, and now you keep compressing and the force does not change. It means that you don't have to, okay, increase the force. Okay? And this is the secret for the reason why this is so pleasant to manipulate. And it made my student, Jacopo Guagliarini, who was studying these things, the most loved member of the laboratory, because he had lots of these and everybody wanted to have one of these to play with. Okay, and okay, maybe so here in the other thing that we find here is that the existence of two end state, because it's when the stroke of our mechanism saturates. There are two limiting angles in this, which is the maximal extension and the maximal contraction. Okay. Okay, so there's a lot of interest in morphing things coming from robotics, these kind of things, and being able to separate elasticity and geometry can be very useful. Now, the next thing I wanted to talk about, okay, let me see. I mean, I'm going a bit slow. Is another instance in which there is a fight between geometry and elasticity. Okay, it's a very humble and beautiful material. So this is okay. This is corrugated cardboard. Okay, maybe you can see it here. So it's a composite material. There is a layer of paper which is unstretchable. It gives our isometries. Okay, And maybe I should have done this. You know, isometries are very bad at draping because they cannot generate Gaussian curvature, right? So, and origami text, I mean, origami has been used as a technique to go around that. And okay, so there is a layer that brings you the isometry. And then there's another layer, which is this corrugated cardboard thing, which is forcing no bending in this direction. Well, no bending, maybe it's a bit extreme, but certainly there's a huge difference in the bending resistance in this direction. The material is very soft. And this direction, the material is hard. And incidentally, Gauss theorem, right? Because the reason this corrugated thing is very hard is because it's a pizza story. So if I want to bend it in this direction, I would have to give a curvature in this direction while the material is already curved in this direction, okay? So this is, engineers call this resistance by shape, but it's really the fact that the material is resisting bending by resisting stretching and not bending. So it's behaving like, I mean, it's listening to Gauss, not to Timoshenko. Okay, and this is a humble material, but you have been, I mean, your life now depends on this material because every time you order an Amazon thing, you know, it's this is the thing that allows you your Amazon packages to arrive at your home, and it's used a lot. The Amazon thing tend to be 2 copies of this, and they are very, very stiff. So I need this because I want to play with bending and stretching. Okay, and then this is a concrete object. It's a very intelligent object that is used by a certain company in the UK as a container for rolls. So when you want a hot roll, you get into this thing. So the roll is here, and you're told nothing, right? So you go take it, and you manipulate it, and you immediately understand what you have to do, and I mean, no explanation, right? Foolproof, folding, unfolding, right? So one interest in these objects in the context where I work, which is a biorobotics lab, is that as you have seen maybe the first day, there's a lot of trial and error. And this is because there is a lot of intelligence in the hands of people who manufacture this. And in fact, it's really when you manipulate these things, it's really telling you a lot. I mean, it's telling you a lot of the way they behave. And so in an effort to try to bridge the intelligence in your hands and the intelligence in your brain by understanding the geometry, we did an exercise at trying to understand how this works. Okay, so the beautiful things about this, so this is used as a container. Okay, so there will be a roll inside. Then it's foolproof. Okay, it goes to exactly one position. If you want to, open, close. Maybe if you start playing with this and you have a pathological mathematical mind, you will start understanding that this is actually on a plane. This sits exactly on a plane. And this may be of interest for the facades, right? So imagine that now you want to make a lot of these, and the fact that they can be in a plane can be of interest, but here it's beauty. And then I don't know what else I want to say about this. The second thing is that actually I got into this through this project, which was about a hygroscopic composite for facades for architectural materials. So this is a composite thing made of many layers, some of which are resistant, some of which are hygroscopic. And we were getting this, and you see that the shape, it's tapered. Okay, so the thing tapers, and we were trying to understand why, because not everybody in the group, I mean, why does it taper? Okay, so these are the questions that we wanted to ask. And so these are the questions and these are the answers. The reason why this is so robust is because geometry, locally, around the curve fold, completely dictates, geometry, yes. And geometric constraints completely dictate the behavior. And there is really just one degree of freedom that generates all the structure, which is the angle at this point. So the folding angle at this point generates everything. Okay, so the reason for the foolproofness of this mechanism is that it's a 1 degree of freedom mechanism. So the infinite dimensional unknowns that generate the shape of this guy all are slaved to one parameter, one scalar parameter, which is this guy. And then the other thing is that the foolproofness has to do with the fact that there is a bistability. Okay, so when you curve this, when you curve it, then there is an energy barrier in between these two configurations, and so there are only two configurations. Okay, so this is resonates with what Katia Bertoldi was saying a few days ago. So this search for bistable mechanisms that are robust, you open up a tent, and here the tent is in front of you. Okay, and this is a tent in miniature. So I don't have the time to. So I will tell you the ingredients that go into this, and maybe the thing I wanted to say is that I will use essentially elementary geometric properties. So with one exception, the fact that what I'm doing is I'm piecing two isometries along a curve. Okay, so everything that comes from here is, not that trivial, and but the rest is geometric manipulation. And let me say what are the main ingredients. Okay, so the main ingredients are, maybe I'll go a little bit into this slide only. So the main idea is that first of all, you have before deployment, you have a flat object on which you can draw a fold line along which you will fold. Okay, so you weaken a little bit the link so that it can fold here. So this is one of the design parameters. Another of design parameters is the direction of the rulings along which the surface will deploy, because they are hardwired into this. And so you see that the things that are at your disposal somehow are the relative orientation of the curve with respect to the ruling, and the angles by which you do. And here it's very simple. This is an arc of a circle. And the angles, these are collinear rulings. So the angle does not change across the fold line. Okay? These are the two secret ingredients of this object here. And now you have to understand where does this rigidity come from, having to piece two isometry continuously across the curved interface. This is what this is about. So for you who are very smart, it's very easy. Maybe I could give it as an exercise, but the thing is that you want to see the same object, which is the curve that separates the two regions, in several possible ways, so that you generate equations that couple the behavior of one side to the other. Maybe I forgot to mention this. The most important thing about all this is that if you have origami with straight lines, you can move this part completely independent from this other, which is very good to make a book. And what you want to do here is the opposite, right? So you want that the motion of this is affected by the motion of that. Okay, and that's what the curvature of the fold does for you. And so what we are going to do is to look at this curve, this one, before folding, after folding. And after folding, it's a space curve. It's a curve in space. Okay? Actually, we are going to prove, I will not. We are going to prove that it's a curve in plane. So the torsion of this curve is zero. Okay? This is a consequence, a direct consequence of the fact that I'm using collinear ruling, but I will not prove that. And now I have a curve in space, and I can look at it in three possible ways. One is if I put my hat of Freinet, and I look at a Freinet frame along the curve, and then I get normal and binormal, and then I get Freinet formulas that link a little bit these quantities. But then I can look at these things in two more ways, actually two copies of the same way, as a curve on a surface. So again, in the same way as I was exploiting the geometry of curves on surfaces for this guy, I can do it here. And then I get another set of formulas. So first of all, I get three different a set of three different vectors. It's not tangent, normal, binormal, but it will be tangent, normal to the surface, and the other guy, exactly as I did before. Okay. Now I can do it as thinking of this as a member of as a curve on this surface, or as a curve on this surface. Okay? And now I have three different ways of relating curvatures and quantities here. And they talk about the same guy, this space curve, and so I get relationship, basically. And so I will not bother you with the details, but basically, okay, so this is Frenet, if I'm Frenet, then I have the formulas of Darboux, and then I have, for example, this guy, the derivative of the tangent with respect to arc length, according to Frenet, is this one. According to Darboux, contains the geodesic curvature and the normal curvature. And now I can equate them and find consequences. And this is the thing that leads essentially to the fact that, there are two possibilities. If this is curved, this can be curved in only two possible ways, either in the same way as this one, or with a minus sign. Okay? This is a direct consequence on this formula. And then you can keep going. Okay, one very interesting thing is, for example, maybe this is so geometric that I can do it. Okay, so this is the equation I was telling you before. Now let me dot this with u. Okay, so this is the third vector of the Darboux frame. Okay, so this is 1. This is normal to the surface, so it disappears. And this will give me the cosine between the normal to the curve and one of the vectors of the Darboux frame. Okay. And so this relationship, so there will be a cosine alpha here. Okay, it's the angle between the. Okay, it's the angle between the this vector u and the normal of the Darboux formula, of the Frenet formula. Okay. And so this formula says that the curvature of the space curve times cosine alpha equals the geodesic curvature, and okay, so something I forgot to say, the geodesic curvature of this, here I'm using the isometry. So the geodesic curvature of this is preserved under isometries, so I can read it here. It's nothing but the curvature of this flat curve, of the curve before unfolding, right? So I read the curvature here, I apply an isometry, the geodesic curvature is the same, and so I know it. It's the radius, it's 1 over the radius of this circle here, right? And so this is telling me that folding, so the curvature times cosine alpha is the curvature of my initial fold line. So this curvature is this divided by cosine alpha. Cosine alpha is smaller than 1. This means that the curvature increases. Folding increases the curvature. This has interesting and devastating consequences. Locally, it just tells you that you are getting curves that are more and more curved, so with radius smaller and smaller. And at the local level, so if you don't worry about global stuff, but just local, there's no problem, there's a singularity. So you can generate a curve with infinite curvature by bending this thing to 0 angle, right? So I take these two things, I bend it, and I generate something whose curvature goes to infinity. At the global level, you cannot do that, because the reason I could do this is because I could shorten the curve. But if this is a closed curve, you cannot do it, and then you buckle out of plane. Okay? And this is just an innocent consequence of what we're saying. And then, okay, there's more things. Maybe the only thing I wanted to still say is that the 1 degree of freedom aspect comes from the fact that there is an ordinary differential equation for the angle, and so the initial condition, so the angle at one point determines the angle everywhere. Okay, but it's a beautiful thing that you know, the fact that you're solving an ordinary differential equation on the angle proves the fact that it's a 1 degree of freedom thing. Okay, so let's jump to the maybe the one last thing I wanted to say is about this cooperativity. Yeah, and so the key thing is that the bistability comes from the fact that the bistability comes from the fact that once I have bent this part, Then I have to overcome a barrier, and then I go to zero energy configuration here, right? And so the natural question is now, what happens if I have many curves, right? Because the relationship between these two is special, and so they talk. And so if I want to repeat this further down, I'll have to do something, right? And so maybe let me show you this little object here. So this is again the same idea, showing that you can generate somehow a preferred folding mechanism. So I can fold this guy, and if I fold it like that, all throughout the path, I have a low energy path. Okay? But if I have done one first, then I have written down in this system an energy barrier that has to be overcome if I want to go here, okay, if I want to bend it. And so this is something that shows you that it's possible to generate a preferred folding pathway in a system using the coupling between two neighboring folds. So the synchronous folding is along a low energy path, while sequential folding, so I fold one first, and now I have to fold the other one, I have to overcome a big energy barrier, okay? And so this is all curvature energy that we have to provide to the system. Okay, so I think I've bothered you enough. Yeah, so maybe this is where this comes from, the second part. It's work that came out of a collaboration in which we were sitting around the table and looking at the beauty of geometry and mechanics and how adaptivity of structures could be captured by this idea. And okay, thank you very much for your attention.
Thank you, Antonio, for your very beautiful talk. Questions?
Yeah, thanks very much. Maybe question on the last. So how important are these corrugated grease cardboards for this mechanism? So if we buy French fries at McDonald's, we get this this thing there as well, and I guess it has similar mechanisms, but without the special material.
No,
right?
They select one specific isometry, so it give you. So how important? So if you do this without the ruling, you have more freedom. You have many more isometries that you can find, and so it's not 1 degree of freedom, I would say. So definitely to reconstruct the whole geometry. I mean, I'm sorry, I didn't have the time, but you need two things. You need the curving space, and then you need the rulings somehow. And you can do it in paper with many rulings, with many different rulings. In this case, this one forces you one. So it's the 1 degree of freedom part, I think, uses the specific ruling. So you can do it yourself, right? I mean, you can on a piece of paper, and then you will find similar things, but much more floppy. Or maybe there was one beautiful remark. So about you mentioned at some point the fact that whether the curvature, Gaussian curvature, determines entirely the embedding or not in higher dimension, etc. So for us, this is a huge thing because it's what we call floppiness, right? So it's the fact that with the metric we can control the Gaussian curvature, but there are many surfaces that can share that, and the possibility of a system to explore that is what we call floppiness, right? It's exactly this. And so what I was saying is that with the freedom of choosing the ruling, you have a floppier system that can have more freedom.
Okay, if there is no other question, we thank Antonio again. Okay, last talk of this morning, we have Helmut Pottmann from Vienna. And the title of this talk is Discrete Differential Geometry of Quad Mesh with Application in Computational Design. Please start.
Thank you. Yeah, I would like to thank the organizers for having me here. And when I got invited, I wasn't sure at all whether my work will fit, but now I realize I think it should fit quite well. And actually, a lot of the things I'm talking about already appeared as concepts in the first talk and some applications in Antonio's talk. So I think it should eventually fit. So the motivation for me to work in this direction was actually from architecture, where maybe 20 years ago, 15 years ago, you saw large, geometrically complicated projects involving whose design, digital design is of course easy, but whose construction on this large architectural scale is a challenge. And it turned out that it is a clever idea to link the design with the fabrication, which means you design so that eventually you can actually fabricate it and not just come up with some nice B-spline surface and then you have the trouble of actually building it. So another idea, and one idea in this direction comes from a German, actually architect and engineer, Eike Schling. He has just some flat, straight lamellas of bendable material like sheet metal, and he brings them, sorry, very sorry. This goes so far. Brings them up in a grid shell-like shape, where eventually these lamellas are orthogonal to a surface. Since they are orthogonal and originally straight, they follow asymptotic curves, and this is a nice idea to combine design and fabrication. My methodology, which I will advocate for today, is to use discrete differential geometry here to represent the objects and numerical optimization to solve actually the problems. I briefly also mentioned one problem in the direction right away because it will come up later at several places, namely the paneling problem. So what you see here on the right-hand side is a design by Zaha Hadid architects, which was never realized because they insisted in building it from glass. And clearly you cannot build it in a monolithic way. You have to break it up into panels, but it is a real freeform geometry. So no matter how you break it up, any two panels are different. But unfortunately for general curved glass, you need a mold to produce such a double curved panel. And this becomes prohibitively expensive. So of course, the solution of this paneling problem also depends on the material which we are using. And I will tell you a little bit about this. What is discrete differential geometry? Discrete differential geometry reacts to the appearance of discrete representations in computational mathematics. We do not work usually with a smooth representation. We work with meshes like triangle mesh, quad mesh. We can, of course, not apply the techniques from differential geometry directly because there is no differentiability. But discrete differential geometry does not go ahead and just discretizes the equations of the smooth theory. On the contrary, it tries to develop a more general theory which contains in the smooth limits a classical theory. But actually, you want to discretize the theory rather than the equations. This is a key thing. And there is, I will concentrate here on quad meshes for various reasons. There is a beautiful book on this discrete differential geometry of quad meshes by Bobenko and Souris. Their focus is on special parameterizations like conjugate, asymptotic principle, and so on, transformations, integrable systems. And maybe what is new in my presentation today is we work with arbitrary quad meshes initially. The response is a bit slow here. Now, overview. I first talk about a first fundamental form in the discrete setting. Then I will talk about how we compute constrained geometric structures. And as an application, I will take this stuff which Antonio just showed us, these rods. Then I will talk about computing mappings between surfaces, developable surfaces, they came up, right? Then we talk about paneling with bendable material, and surprisingly, you can do a lot with high approximation quality using surfaces of constant Gaussian curvature, which implies also that you need only a few molds. And finally, I talk about shape morphing mechanical metamaterials. So this is the plan. Now I start with quad meshes, and we start with something basically trivial. We have a quadrilateral here, this quad. We take the midpoints of the edges, and they form the sides of a parallelogram, sometimes called Varignon's theorem, but it's completely trivial because if you connect here two edge midpoints, this by the intercept theorem is parallel to this connection, which is a diagonal in the quad. So this parallelogram has sides which are parallel to the diagonals of the quad. Now we have a quad mesh, and in each face we insert this mid-parallelogram, and we get what I call a checkerboard pattern of parallelograms. So we have actually several meshes that play a role here. Our original quad mesh, this is this yellow thing here. Then the checkerboard pattern of mid-parallelograms. But we know that the edges of these parallelograms are parallel to the diagonals of the faces of our original yellow mesh. And these diagonals form two meshes, diagonal meshes here in red and in blue. So please note that, for example, this white face in the checkerboard pattern here is just a scaled version of a face here of the blue diagonal mesh, and so on. So this we will need later. Now we view such a checkerboard pattern of parallelograms and the quad mesh as an image of the parameterized over a grid. Here is a regular grid in the plane. Then we have corresponding faces. We have corresponding inscribed parallelograms, which here for the regular grid is of course a square, and the mapping here from this square, for example, to this parallelogram is an affine map, and it is just a discrete version of the derivative map that we have from the parameter plane to the surface, the discrete surface, the discrete derivative map. It is useful to put the u and v direction here into the diagonal directions, and then you could actually say essentially the diagonal vectors in a face here are the partial derivatives, discrete versions of them of xu and xv. More precisely, if you assign them to the center of the corresponding quad in the parameter domain, you have here central differences, and you have the second order approximation where h is the grid size. This means we have a first fundamental form because we have in a nice discrete way come up with first derivative vectors, and we have, I use even the Gauss notation EFJ, inner products. It uses a diagonal parametrization which has several advantages. On the theoretical side, I'm not going into this detail, but one could use, for some cases we even do it a different way. We also assign this first fundamental form to a face rather than a vertex. Face is much easier. And we take just connections between corresponding opposite, I should say, edge midpoints. This is also working, and for practice is almost as good as here. But please note, to define this vector, all four vertices enter in the computation, and here only two enter. This makes already a slight difference. Now, I want to show some examples for how you may use it. And the first thing we were thinking about is angles between parameter lines. So what you see here is a quad mesh. It is a discretization of a parameterization with respect to u and v. And we have these isoparameter polygons here, while in the smooth case it is completely trivial to find an angle. So what is the angle here? How do we discretize an angle here at such a vertex? In space, we have, of course, four different angles. So what is the angle? How do we define it? And you here see one application of such a quad mesh, actually here a case with planar faces. And I will talk here in my example also with quad meshes that have planar faces and right angles, which turn out to be discrete counterparts of curvature line parameterizations, which also came up, of course, in your presentation. Now, planar quads at first. No, the angle first. Angle is already shown here. Because we use the diagonal meshes, actually, that are the meshes of interest, and we just look into a face, think about the first fundamental form I explained. The angle is just the angle between the diagonals. If we want the right angles, we want the right diagonals, which means our checkerboard pattern is formed by rectangles and some white faces, which are maybe close to rectangles, but of course not exact rectangles. Now, planarity is also easy because we know that each white face here is a scaled version of a face in a diagonal mesh. So we get, in this checkerboard pattern, we get actually planar quads if both diagonal meshes have also planar quads. So we have now 3 planar quad meshes, namely, and a planar quad mesh, I should point out, is something related to the second fundamental form. It is a discrete conjugate parametrization, right? So these directions in the smooth theory are orthogonal with respect to the second fundamental form. This is this conjugate. So we have 3 of them, this checkerboard pattern and the 2 diagonal meshes. For practical applications, it's not exactly the same, apart from the fact that this the diagonal mesh is, of course, coarser than this checkerboard pattern. But if you look carefully at this parameter line here, it is a bit zigzag, which for certain application is already not so great anymore, while here this is a bit fairer. So how we get nearly rectangular faces in such a quad mesh with planar faces? Of course, exact rectangles in general do not work, except for cylinders. There have been 2 structures investigated in discrete differential geometry. One is the Möbius geometric version, where we say each quad has a circumcircle. This is an orthogonality condition, right? This is a kind of orthogonality condition. And the second one is a conical mesh, which we developed by motivated by architecture, where we say that in each node, in each vertex, the 4 planes which meet there, we have now planar faces, are tangent planes of a rotational cone, a right circular cone. I just use this figure to illustrate a little bit this way of thinking in discrete differential geometry. You have here, with this rotational axis of the cone, you have well-defined discrete surface normals. By symmetry properties of the cone, you will find that those cone axes which belong to the endpoints of an edge lie in a plane. This means you go from one discrete normal in this direction to the other one, and they intersect. This, you can do it over the entire mesh. This shows already is a principal curvature parametrization because it's well known. A curve on a surface is a principal curvature line if and only if the surface formed, the ruled surface formed by the normals is developable, right? And this is nothing else than discrete developability. Of course, you can also see it as an eigendirection in the Weingarten map, shape operator. Yes, right circular cones, rotational cones, yes. Yeah, sure. And by the symmetry, you see that this lies in a plane, right? Okay. Now, while it is not completely straightforward to come up with these orthogonality constraints, it is totally straightforward now because we just have, in addition, to take orthogonal diagonals, right? We have a pair of meshes and we choose orthogonal diagonals. So this is a lot easier. Then we have actually 3 what we call principal meshes, discrete curvature line parametrizations, namely the checkerboard pattern, which now is formed by black rectangles and here white planar faces, but not exactly rectangular. Please note the appearance of combinatorial singularities, which here would be at flat points. And we have the 2 diagonal meshes, which are also principal meshes. And of course, every surface can be approximated by such a principal mesh, and computationally, we would initialize our optimization by taking our given surface, compute principal curvature directions at a sufficient number of points, then apply a remeshing algorithm from computer graphics, which makes sure that the edges of this quad mesh follow roughly these principal directions, and later you optimize, for example, towards a conical mesh, or in this case, checkerboard pattern, and so on. Here is an example, which is slightly more special because here these are the black rectangles, in this case they are glass, and they're actually squares, which means this is a conformal principal curvature parametrization, which is called an isothermic surface in differential geometry, while the previous case can approximate any shape. Here, this is a shape restriction, isothermic surface, of course. Here we can start to play now with this diagonal approach. It's now super easy to say what is 60 degrees. The circumcircle will not help us for 60 degrees, but here it's super easy to do it as well. So it is a conjugate net where the parameter lines form 60 degrees. Now, how do we compute these structures? Let me briefly talk about it. Essentially, it's a constraint solving problem. So we have certain constraints, like the faces of a mesh are planar, like planar quads. They possess a circumcircle, or certain edges have diagonals from a given angle. This we had already, and we will see more later. And what I tell you is something which comes out from our observations. I talked to experts in numerical optimization, and what we use will not have a theorem that is good enough to prove really our observation. But what do? We try to, wherever possible, to introduce auxiliary variables if necessary, so that our constraints are at most quadratic. If we are not able to do it, we try to come up with geometric ideas to make them at most quadratic. Why? So the thinking is this: we eventually use a regularized Gauss-Newton algorithm where in each step you linearize your constraints. And if you just throw away a quadratic term of a constraint, are different things than if you throw away higher order terms as well. But this is hand waving, it's not really a proof. But then we need to make the thing robust, and we need to make it applicable for our setting, or in terms of discrete differential geometry. Interestingly, there is a lot of theory which would apply even to very weird meshes, but you would not like them as a discretization of a smooth surface. But here, when we apply it in architecture and other scenarios, we want to have a fair result, so this will come into the regularization. Now, example, we want to express planarity of a quad. We could just, without auxiliary variables, take 3 vectors in the plane and write down a vanishing determinant, right? This would be okay, but we don't do it. We take a normal vector and we write down the orthogonality of the normal vector to the edges, to the sides of the quad, which would be alone a bad idea, because then optimization would make the normal vector a 0 vector, so we have to normalize, of course, this normal vector to avoid this degeneracy. Now I mentioned something which comes up often. We want to approximate a given surface by some kind of structure. So maybe the mesh vertices have to remain close to a certain surface. Then you can analyze in a square distance sense, right? Many people do this. They take a vertex in a current iteration, take the closest point, and then in the next iteration make sure to stay close to this closest point. This is not a good idea. Because if you analyze the squared distance function of a surface at the surface and take a second order approximation, you get the squared distance to the tangent plane. So we take then the tangent plane here it is, and in the next iteration we make sure that this VI stays close to the tangent plane. This is this term, right? Projection onto the normal. And maybe as a regularizer we take a little bit of this closest point distance. So geometric is easy to understand. We want to have that these mesh vertices can glide along the surface. And with this tangent plane distance, you facilitate it easily. And if you fix this closest point, this happens too slow. At least you get a very slow convergence. And in some cases, you get actually nothing. Yeah, exactly. Absolutely. Yes. This is exactly the case. Now we want to have a nice mesh. You see these two here. And this is a mesh polyline which resembles somehow a smooth curve. This is too much zigzag, I would say. So if VI, Vj, Vk are 3 consecutive points on such a polyline, we take just second differences, square them and sum them up. Of course, this is not a 0 residual term. So if you get 0 for a polyline if and only if you have regularly arranged points on a straight line. So this is just a regularizer which comes already initially with a small weight, and as you will see now in later iterations it goes away. So at the very end we square all these constraints. So sum of squares method, we minimize an objective function of this form, the constraints, the hard constraints, the fairness term, and this Levenberg-Marquardt regularizer, which makes sure that the step from one to the next iterate isn't too big. So this X comprises all variables, including the auxiliary ones. So this is not a problem here, but this is a problem because even if this mu is small, in the end, this may fight against the constraints. So in later iteration, we set it to 0. This goes away. And this works well. And I show an example of this method for the equidistant curves on a surface, because as I remember in Marino's talk especially, he pointed out they want to solve an inverse problem. Can we achieve any shape with this thing here? What are the restrictions of shapes we can get? This is closed. I cannot. This is really a tube. But if you cut it open, right? And equidistant curves on a surface. The first thing which you observe is, if you have a family of equidistant curves, these are the black ones here. They are level sets of a distance function to any of these curves, right? Constant distance on the surface. This means that the orthogonal curves always go in directions of shortest distance are geodesic. So it's important that the orthogonal curves are geodesics. So we actually look for a parametrization of a surface which is called geodesic parallel coordinates. It's some generalization of geodesic polar coordinates. Maybe it's also in Gauss's work already. Yes, yeah, see, also in Gauss. And we have to come up with a discrete version, right? This is what we want to do. And here it is. Here the constraint, I use here a different way. Not this checkerboard pattern. We have a quad mesh. It's pretty clear where the quad mesh comes from, right? Actually, this can be already an image of a quad mesh. And at the vertices, we have this angle equality. So these angles, these two are the same, and these two are the same. So why? And here, I should say, this polyline here is considered to be the discretization of the geodesic. So why is it geodesic? You see it immediately, because if you go on this side, you have alpha plus beta, and on this side, you have alpha plus beta. So you do not turn more to one side than to the other side. So you would have discrete geodesic curvature 0. You can also see, because of this symmetry here, that this discrete osculating plane, which is spanned by these two edges, is orthogonal somehow to the discrete surface, which also came up in your talk. Now we have the variables. These are the vertices, Fi. Yeah. We want to have unit vectors also as auxiliary variables, unit vectors along the edges, actually half edges, oriented edges, and edge lengths. And then we have the constraints that express really that these Eij's are the lengths of the edges with vertices Fi and Fj, and Wi are the lengths. These are these two equations. And then, of course, the angle constraints are just inner products. So this is quadratic. And this is very nice in the optimization. And in fact, it works pretty well. So here you see some results. What you see here is a surface which is actually a deformation, an isometric deformation of a rotational surface. So it is cut open here and deformed. And you nicely see here by the coloring these strips of constant width, which one would need to solve the inverse problem. So I think the hardest part of solving this inverse problem, by putting a family of equidistant curves on a surface, is to avoid some singularities. Yeah, you can say I can in principle choose any curve at first, and then I advance the front with constant speed to both sides, but then these fronts may meet, and this is no longer physically realizable. So the initialization will be also important. One has to think about. Now I would continue with this checkerboard idea, this first fundamental form. We do have something on the second fundamental form as well, but I will not talk about it today. Namely, quad meshes for mapping between surfaces, and we have only this first order analysis. So we have two surfaces that are mapped to onto each other, and for local analysis, it's sufficient to assume that this happens by equal parameter values. So x at uv maps to x bar at uv. And then we have the derivative map, a tangent vector here, linear combination of the partial derivatives maps to the corresponding tangent vectors there. Same linear combination for the partial derivatives on the other side. And of course, the coefficients here are the direction in the parameter domain. And an isometry, then this mapping from this tangent plane to this tangent plane is a rigid body motion. For a conformal map is rigid body plus uniform scaling and so on. So we just look onto that. So conformal map, derivative map is a similarity, of course preserves angles, and this has received a lot of attention in computer graphics, for example, for texture mapping, but also for other applications. I will focus here on isometric maps, where this derivative map is a rigid body motion, of course preserves lengths and angles. It's pure bending, no stretching, of course preserves Gauss curvature. We have an entire talk about it, how Gauss proved it. And it's very important for the following: if you have two surfaces with the same constant Gaussian curvature, they are locally isometric. So here this is sufficient actually. Here, I want to show an example. We have a sphere, and I show here an isometric deformation of a sphere with a method that I will outline in a few minutes. Yeah. You see here a kind of rendering composed of these elements. Here on this parameter net, we see curves of constant geodesic curvature, which will also be here, of constant geodesic curvature. We see geodesics orthogonal to it. Also, again, an example of the fact which I said before: if you have equidistant curves, like here, the orthogonal curves are geodesics. We also see this nicely here. And for the paneling problem here, for example, with sheet metal, we like to have this situation. We have only a few molds. Here we need a single mold. It needs to be a sufficiently large part so that I can form every tile here over this mold. I take the sphere, right? And I shape the sheet metal over the sphere. And then theory says I can take this and just by bending, glide it over any surface, actually in a 3-parameter motion, which has the same constant Gauss curvature, right? This is the theory. And of course, this has been constructed with the same Gauss curvature. So actually, a single mold is here sufficient. Now, how do we compute it? I think this is already clear, because we have these derivative maps around as maps between these parallelograms, or with help of these diagonals. So corresponding diagonals for an isometric map have to have the same length, same for the other, same length, same angle, right? This is a constraint. This implies that this inscribed parallelogram is just transformed to this one by a rigid body motion. But here we have isometric map, yeah? And then you can write down in constraints, and it's again quadratic. Likewise, for conformal, we have to add here a scaling factor, which I do not need here. And then we do our standard thing. We square up we sum up the squares of the constraints, add proximity to a reference surface if it is needed. As I explained before, we have fairness. Actually, fairness is important. We may get things like this, auxetic behavior. So it's really important. This is always important, but here this auxetic behavior can come up, and here are some results. This is a mapping of a double curved surface with positive and negative Gauss curvature to the plane. Computer graphics guy calls this the parametrization from here to here. And then you have a pattern here. This is yellow thing with this black and red squares. This is not the parallelograms in my mesh, of course. And you go back and you hope that it is not distorted too much. So it is conformal, it preserves the angles, and as isometric as possible. It's not a hard thing to do with this approach. Or you take any CAD system and deform this can into this shape. This is not an isometric deformation, of course, you see immediately. But then we can make it isometric by our method. You see this buckling behavior, which you also see on a can, for example, which you have. Another example, isometric deformation of a rotational surface. You cut it open, you can deform it, while this does not go through as a kind of free-form shape for architectural applications. Also, the intrinsic geometry is, of course, the same for all of those. This goes more through like free-form. You do not see this anymore, so it's not so easily visible from outside, whether these are intrinsically the same, these surfaces. And of course, for the paneling problem is a huge advantage, because if we have a rotational shape, along these rotational circles, we have same mold, in this case, even congruent panels. And so we need only as many molds to panelize this as we have strips here in this arrangement. So this is also an advantage for panelization. And that's, here I have an example. Now I come to developable surfaces. I forgot which mathematician did it first. Euler, yeah, okay, Euler. And so we'll talk about developable surfaces, which are surfaces that they're isometric to the plane. So we take a sheet of paper and we bend it, right? And these are the developable surfaces. And we'd like to compute with them. I saw this, was it also in Euler? A developable surface is in general locally the tangent surface of a space curve. I think you also had it. This is here. The space curve itself is singular. Not good for applications, but this is a nice part. And there are special cases like cones and cylinders, and of course a plane. So a general developable surface is, with this smooth, a composition of, I think you need C2 actually, of cylinders, cones, and tangent surfaces of space curves. Not all ruled surfaces, of course, are developable. The important property really is that along such a ruling, you have a constant tangent plane. And since you have this constant tangent plane, if you bend this piece of paper, the silhouette of this piece will always be straight, because a silhouette means that the tangent plane passes through your eye, and then it happens for the entire ruling, right? You see easily. Now, the simplest discrete model would be this. We take just a strip of planar quadrilaterals. Of course, we can unfold to the plane. This is obvious. Just taking this intersection of transversal edges, actually you find this discrete regression curve, right? So you can even come up with a derivation of this property. And if you refine, you get better approximation. But this is not such a great idea for some things. Like if you take this piece of paper, I can deform it, but these rulings change all the time, right? So a ruling-based discretization is not good if we would like to have general isometries of the plane. Antonio, you had, of course, the rulings because you didn't want general, right? You wanted to have this cylinder. But if you want general, no ruling. So we do not want the rulings. Here are some examples which are obvious. I do not go into any detail here. There was a first idea in this direction came by the group of Olga Sorkin-Hornung at ETH Zurich. Say that a surface which carries an orthogonal family of geodesics is developable. This is easy to say. And they discretize this. And then they can somehow model this nicely. And actually, from what I said before, this angle constraint, now both polylines that go through should be geodesic under a right angle. Previously, we had these two are equal and these two are equal, but now we have all four are equal. So this is now the constraint, just these four angles. And then you can conclude that this has local symmetries. There is a well-defined discrete normal. The discrete oscillating planes pass through this normal and so on. So it's really nice discretization of the theory. Later you can, when you model it on the computer, you can fit the rulings. You will see the rulings are there. They must be there. But they are not used in the actual computation. I think this is here important. Our approach is in a sense more flexible because, of course, we define a discrete developable surface is a quad mesh, which is isometric to a planar quad mesh, right? In the sense I had before, namely corresponding parallelograms, if you like, are congruent. If this planar quad mesh here is agreed, then it's equivalent to what I said before, but it needs not be, it can be any quad mesh in the plane. Here you see what happens if we do not apply fairness. Well, we get something like crumpled paper, but we do not get a smooth surface, right? So this may even be useful for something, but with fairness, we see. So it's a bit slow. Here I want to show you, because if you present this in certain communities, it's always good to have a physical model. Even in computer graphics nowadays, rendering is nothing, right? If you do something related to fabrication, you have to have a physical model. And I show you a physical model of this discretization. A discrete developable surface, which is isometric to a regular grid in the plane, is nothing else than a checkerboard pattern of congruent squares, black squares. So we build it. These are the black squares from some material. They are joined here by spherical joints. So the shapes you can get are developable shapes. Then you must be able, if you take some developable surface, you must be able to glide this thing on the surface, and you rotate it in the surface, and let us see whether this really works. So see, no attachment of this direction to the rulings at all. You can play around it. It always fits well. So this shows actually it's just a physical model which shows that even now this is just something to show to the computer graphics guys, right? It's nothing else. Yeah. It's physical. Now this is physical. Yes. No, of course. Yeah. Sure. You have to build it. No. Yeah. No. We did not render these hands and so on. No. This would be. It is less work to build the physical model. Yeah. Sure. Yeah, and then you can check whether our discrete developables have the properties we want. The Gauss image formed by the unit normals must be curve-like, and you really see this curve. Of course, there are some small deviations because of discretization. You can fit rulings. You can apply an affine map. An affine map is not an isometry, but it must map a developable to a developable, because rulings go to rulings and tangent planes to tangent planes. So it's clear. Development changes dramatically. So you see we have an affine map from here to here, but the unfolding, of course, is changing dramatically. For computer-aided design, it is interesting to design B-spline surfaces which are developable or numerically developable, right? Yeah. Exact is too restrictive. Yeah? And the idea here is these B-spline surfaces have subdivision algorithms. You have the control mesh, which is this blue stuff here, and then you have some steps of subdivision, makes it finer, and then you optimize the control mesh, the blue mesh, so that after, let's say, 2 rounds of subdivision, the resulting finer quad mesh is a discrete developable in our sense. And this gives developable surfaces with sufficient accuracy for applications. Or you can do these things. I take 2 sheets, let's say, of paper, convex here. Perimeter of this is the same as this, and I start gluing them together, and then I get the shape which is called a D-form by, you may know him, a designer, Tony Wills, I think, you may know him. Huh? And then this agrees very nicely with the physical model. And you see here the mesh also has some combinatorial singularities, and the mesh is, of course, aligned with the boundary. These are all things you could not do with this discrete orthogonal geodesics, but you can nicely do with this more general quad mesh approach. If you take one lamella here not convex, this is not so nice anymore. Both the theory, the physical experiment, and the computation say then you may have some buckling here. Here are some other examples. So like this one, you have this flat sheet. We cut here these holes. Again, this length is the same as this length, likewise here. And you try to close them, and you check whether the model is able to do it. And it works actually quite well. Yeah. It's not so hard to do. And again, we check with a physical model. Or we had curved folding before. You mark a curve along which you introduce a crease, and we want it to end here. So it fades away. The crease even fades away, and here it is. These things you can nicely model with this approach. A simplest characterization of such a crease is that the osculating plane at each point is an outer bisecting plane of the tangent planes on either side. So this is the simplest, because then you have the closing in the plane. Geodesic curvatures are the same up to the sine, so the curvature circle is the same. I think this was underlying your formulae. Yeah. Then maybe I skip this. And now we go to, we are in time paneling. So we solve the following problem. Given is some surface and already a patch layout. So the panel boundaries actually are given. And we would like to approximate each panel here by a surface with constant Gaussian curvature, but we would like to have only very few curvature values because we want to have only very few molds later on to produce them. And here's a solution. The color indicates the Gauss curvature, so reddish is positive, bluish is negative, and white means developable. So this is an approximation. So there are some kinks here in between, kink angles, but they are small. We do not see them well. So we assume that the material allows for isometric deformation. It's true for certain plastics, for sheet metal, and so on. Now, if the Gauss curvature is positive, of course, the mold will be part of a sphere with radius 1 over square root of Gauss curvature. If the Gauss curvature is 0, need no mold, the panel is developable anyway. And Gauss curvature negative, we could choose a mold which is part of a pseudosphere, but we could choose any surface of the correct value of negative Gaussian curvature as a mold. And the algorithm, I just sketch it. There is some details which is not as trivial as it sounds here. Curvature analysis is trivial. We could put the mean value of Gauss curvature in each patch. Then if this is close to 0, we will later work with a developable panel. And then we do k-means clustering on the mean value of Gauss curvature. In this case, you choose the k, right? We choose a small number. K, I think we have 10 in all the examples. And this gives a small number of curvature values. Then you can compute the molds. This is easy, a sphere or pseudosphere with the right curvature. This is the harder part. We have to optimize each panel so that it stays close to the design surface. And an isometric copy of it is close to the mold. So it's a kind of, we call it a registration problem. We need this proximity term, which I mentioned, and a few other ideas, but I don't want to go into that detail. But this is actually the hardest part of the whole thing. And we could, at the very end, do some global optimization to reduce the kink angles at the panel boundaries. But to me, the results were very surprising. So here it almost looks like a smooth surface. So this is not a smooth rendering, where you blur away the deficiencies at the boundaries. It's just you render the individual patches. Yes? It needs not even be exactly continuous, because in the application you have seams and you may have very small deviations also in continuity, right? But you don't see it here. This is super small, yeah. This is actually this paneling is always somehow playing with tolerances. But here the interesting thing is that constant Gaussian curvature has such a good approximation quality, and it apparently also does not depend much on the layout of the panel. So we have the same number of molds here, same number of panels here and here. Approximation is roughly equally good. If you have more panels and still with the same number of molds, you get a better approximation, of course. Yeah? And it's not a linear approximation, what is actually higher, but very hard to analyze. So I returned to this design, which was never built, but it won the competition. This happens in the area because what is submitted is actually just rendering and digital models. And we wanted to try it here. And it worked relatively well. Look at these big panels here. There is some deficiencies. You see it mostly here. Here you see really a king, right? So it's very, very visible. Here is something. So, but overall, it looks good, and the panels are way too big. In practice, you would take smaller ones. And you have only 10 molds. It's real data. This is also real architectural data. You may ask, where do I have them from? We had a small company which did some consulting for architects, and therefore we have these models around. Yeah, yeah, yes, on purpose, of course, because if you have higher curvature here, yeah. This we took from our company, have done that, but in this algorithm, it is an input. But it's a very good question. Of course, you could try to have an algorithm which also computes these boundaries. Also, in some cases, well, here, the boundaries are not that visible, so it's not so much of a design task, but if the boundaries are clearly visible, then it's also a kind of design task. So then the architect wants to have some influence on it, yeah, in a certain sense, yeah. This also is this build structure in, I think, in Baku. Again, we had a physical model. So this is the design. It's not a nice surface, but we applied the algorithm. So this grayish stuff is developable. Reddish is negative curvature and blue is positive curvature. Then we have two blue panels here over the same mold, same Gauss curvature value. So this is the corresponding mold, it's part of a sphere. I will tell you in a moment how you produce the panels. Here is a negatively curved mold and the 3 panels which are needed for that. And here is the final object mounted on a frame. And here you see how these panels are formed. It's called thermoforming, and you will know it much better, Antonio, than me. So you put here some plastic material, you heat it up, does not go as fast as in this video. And then you lift up the mold and suck out the air, and then this attaches to the mold. And then you take it away and you cut, of course, out the correct boundaries, and then you will get, yeah, the result here, put it on the frame. And then, yeah, it looks as the original design, not beautiful, but it nicely meets the original design. And very quickly, I talk about the design of mechanically metamaterials. This was inspired for me by work done in Mark Pauli's group. They have a material which originally, let's say, is shaped in the shape of a regular triangle mesh, and you cut the edges, but you do not completely cut them. You leave a little bit out of materials there, so that this little bit of material acts like a rotational joint, right? And then you have a completely closed state, which is this triangle mesh, and you have a fully open state, which is a mesh. Alice had this Kagome pattern. And if you look, this always stays, yeah, if you open it like this, there would be other ways, but if you keep this kind of rotational symmetry, then you have here the centers of these triangles on some circle, of course, and here of a circle which is twice as large. And then you could argue that the behavior of this material is a bit like a conformal mapping, where the scaling factor can be at most 2, right? From here to here, at most 2, it can be less. And then, and you saw here an example. And actually, I do not know how they could actually do it, because this is not so easy. You have your triangle stuff, and you have to get everywhere the correct scaling with a mold. I would know how to do it without the mold. I have no idea. Later, they had something where the final state is fully open. This is easier, but since the original state is not fully closed. And then I saw a paper from Mahadevan's group in Nature Materials, and I saw these results. So it is also kind of mechanically metamaterial, but the results do not look right. Some of them look too unfair. And then you look into how they are solving the underlying optimization. Of course, it will be optimization. And they initialize the optimization also with the idea of a conformal map. And I think it's not the right way to do. And so we tried something else. We tried to analyze it more rigorously, slightly more geometrically. And then we have two shapes, an initial shape and a target shape. And we would like to design the mechanical metamaterial so that the initial shape is in the fully closed state and the final shape is the fully open state. So we wanted to see whether it works. The first is a kind of first order approximation by a rectangular grid. We have these four rectangles here. And of course, the centers also is a rectangle of lengths A and B. And if you fully open up, clearly the centers of the rectangles form a square. The diagonal of a square is A plus B. So we have the side length is A plus B over square root of 2, which means actually we do have here, first of all, this is an orthogonal directions, which is also here orthogonal directions. If you have a map between surfaces which maps orthogonal one pair of orthogonal directions to orthogonal, say as a principal distortion directions, of course, right? And so the principal distortions are A over W plus B over W, and they sum up to square root of 2. So you have a kind of constant mean distortion map. This needs to be built in, and of course this here on the right-hand side ends up in a kind of conformally mapped square grid. And then the following simple idea already worked. We do this constant mean stretch between the fully closed and the fully open in some kind of parameter domain. Then to initialize the optimization, we map this as isometric as possible to the initial state, initial shape, and this as isometric as possible to the target shape. This gives you an initial closed state of this metamaterial and an initial open state, say initial before optimization. And then, of course, you have to make sure that corresponding phases are really here congruent, right? This is some optimization, and quite some detail goes in. I do not want to go into that, but I show you some animations, fully closed to fully open. So it really worked. Or here, fully open, and here the fully closed is flat. Or, yeah, a smaller example, but this was actually built. This is not fully open. Unfortunately, I do not have the photo of this fully open, but I have this. This is a fully open case, and there we checked with a mold where we put it, whether we really get the right shape, right? And it is the right shape. So I'm done, actually. I just want to conclude. I think that there is here some kind of interplay of the theory and applications of discrete differential geometry. I was focusing more on computation and applications, but there is this theory behind in topics in computational design and fabrication. What I like that with this discrete differential geometric way, the variables you have are really the design variables you are interested in. They are not some numbers in some discretized equations, and easily transferred to optimization. We always prefer to discretize the geometric theory and properties preferred over the numerical discretization of equations. So many problems here would, of course, come in the form of some not so nice nonlinear partial differential equations, and we as geometers, applied geometers, prefer to do this. I could show you some examples where the difference is huge. And finally, personally, I also like a little bit to work at this interface of technology and design, or mathematics and design. So I like if beautiful shapes emerge, right? Somehow this is nice. And with this, I would like to close and thank you for your attention. Thank you very much.
Thank you very much to brought this beauty to us. So are there questions?
Sorry, I have a very naive question to see whether I understood correctly.
Yeah.
When you say that you need a mold with given curvature, you really mean just the Gaussian curvature. So the principal curvature, you take them to be equal. So you take pieces of sphere.
What I talked about in the last part?
No, before.
I had several molds appearing. But whenever we have this, the last part, I mean the molds with constant Gaussian curvature surface, right?
Yeah.
There, only the Gauss curvature mappers by Gauss theorem, right? If I have, I generate a patch with the correct Gauss curvature, and then I can take it and I can attach it to any surface with the same constant Gauss curvature. I can even move it around in a three-parametric way. This is elliptic plane or hyperbolic plane, of course, and I can move this around, and this I use. Of course, I have to, this may be important, which I did not mention. The mold is a bit bigger. You saw it also in my video. And then I have to cut it out in the correct way, right? This is, yeah, this you have to do. Is a lot cheaper. Yes, of course. Yes, yes. I make it big enough so that my biggest panel, so exactly. And it does not even matter where I place it, right? Because I just cut it out, yeah.
I think it's a related question. For the glass structure for
glass is a very different thing, yeah.
So if I just bend glass, it would break as well. Even
this is a very good question. Yeah.
So should you put a limit on your change in principal curvature in addition?
Thank you for this question. I mean, the glass is a totally different thing, and we do have one paper on glass. And this is the only paper where I used deep learning, and I tell you why. Because, of course, you can run a simulation, how the deformation of glass behaves, and you can incorporate the limits of stresses when it will break. It depends on the type of glass, on the thickness, and so on. But we wanted to have something which we can combine with the design of the shape. Would take a bit to find it here in my computer. And it turned out that, I mean, it's not an elegant method, so I'm really not proud of it, but it works. You can run, let's say, 1 million simulations to learn which shapes are possible and which are not. And then, of course, you have these differentiable results, this neural network. Actually, there was some interesting thing because this network later could also predict whether there are two potential states of this piece of glass, which I can push to the frame so that it does not break. So even this came out. And then you find out that you can actually create quite some interesting shapes with this slightly cold bend glass, right? This is what you are talking about. You want the cold bending, and the architects prefer the cold bending. Actually, the glass, when you heat it up and put it on a mold, it is afterwards not as nice anymore as it was before. And even putting it on a mold, in general, is critical if this is a double curved mold. So the only glass panels which work nicely, as the only surfaces, I should say, where the fabrication, heating the glass works well are essentially cylindrical shapes and spherical shapes. This is because during the cooling, you need somehow the panel move in itself. You need surfaces that can move in themselves. And if you want to see an application where this was used, we had once a project in Paris on the Eiffel Tower. If you go to the first platform, you see 3 pavilions with glass facades. The underlying thing is actually a conical mesh, which I briefly mentioned here. But it was realized with single curved panels with cylinders coming out from some optimization. Right? So glass is a delicate thing, and it is clearly for double curved elements. Yeah, I think that the cold bending is one way to go, but this did not make it into the application yet. It's not true that when you bend glass, the result is cold bend the glass, the result is close to developable. It's not true. Yeah? You can look at the Gauss image, it's not curve-like. It does not like to bend to be formed into a developable shape.
Helmut,
yeah.
Relatively at the beginning, you showed 1 or 2 examples where a quad mesh was not sufficient due to topological reasons, where you had some panels with
right. I had these combinatorial singularities, right?
Right,
yeah.
and you placed them at zero curvature.
In this case, yes, it was negative curvature. I mean, this was this very important thing, yeah, if you want to, it is always good to know the smooth limit of something, right? If you say, I want to have nearly rectangular panels, yeah, flat panels, this does not tell you, but if you realize that this is a discrete version of a principal curvature parameterization, you will see where are the singularities of the curvature line parameterization at the umbilics, special case flat points, and this is where they will pop up. There's a different thing because there is always a bit of mistake, of course, in these remeshing algorithms which you have, right? So we do not do the remeshing ourselves. It's actually a difficult topic to do quad remeshing. And the remeshing may use more such singularities than you actually need, and then you have to live with them. We do not want to, and we cannot do it, we do not want to change the combinatorics in our optimization. So the combinatorics, I would say, comes from the geometry. Mm-hmm. And whenever we have no idea how to figure out the combinatorics, we are pretty much lost. But then almost every other algorithm is also lost, because then you have to optimize over the combinatorics and you want to have a nice result which still fulfills a lot of additional constraints, right? Yeah.
Even if I didn't ask the question, you more or less answered it. So the question would have been...
Aha, I thought this was a question. I'm so sorry.
That, if there's any efficient algorithm to place this topological
that's a good question. There are algorithms which claim that they place it the best way, but the algorithms work well when the angle is 90 degrees. As soon as you have other fields, we call it cross fields, and it not be 90 degrees, other fields, not even constant angle, the algorithms don't work so great anymore. Then we use ideas like this to transform to a surface where they are almost orthogonal, maybe even in a higher dimension. Then you do the remeshing and then you transform back. This is also some people consider this remeshing problem solved, but it's always the bottleneck somehow to get the combinatorics right. Yeah.
So in the part in which you were using molds, so in the part about paneling static structures, right? So you were using the fixed Gaussian molds, Gaussian curves.
I prescribe actually the number of molds.
And then you were exploiting the flexibility of material, so the floppiness somehow, the fact that you could bend a little bit, and then at some point...
No, I assume that I can isometrically deform the material, which may not be exactly true, right? But that's the assumption. It's purely geometric.
But you change components of the second fundamental form, which is not the determinant.
It's not involved at all, right? The second fundamental form is not involved. Well, indirect is always involved, but not computationally, because I only need to make sure that my panel fits to the target, to the surface which I would like to panelize, so it's close to the design surface. An isometric copy of it fits close here to the mold, right?
Yeah. So sorry, but
I may actually be able to change the Gauss curvature value. This would be possible, right? During this optimization, but slightly change it. Yeah.
I wanted to ask another thing. Then at some point you allowed yourself to cut the panels.
Yes.
Okay. So all these is perfect for like one design, right? A static surface.
Yeah.
Then instead, when you move to the morphing part, of course, these things start you cut for a certain shape. And but did you do some work also on how should I say, the shape of deciding which is the range of shapes that you can accomplish with certain specific paneling when you want to change the...
The only thing where we had some kind of animated meshes subject to constraints, but because this metamaterial is in a sense easy because you cut holes, right? Say holes open up, and this is why it is a relatively easy problem. But the problem of, let's say, this we worked on very recently. If I search a bit, I may find something. We have a quad mesh. This is related to your origami stuff. You have a quad mesh, and the faces are rigid, but the edges act as rotational joint, as hinges. And then the question is, which quad meshes are flexible? This is an open problem since a long time. There are old results by Voss and Sauer on special cases. And there is an 80-page long paper by Zmestiev on characterizing the 3x3 configurations. But there was actually nothing on how to glue them together to larger designs. And there we came up with optimization algorithm, which of course, the hardest part is the initialization, right? To get an initial guess, then you can optimize towards numerical flexibility. This is not a big deal. And this would be a separate talk. What worked really well was we went into so-called isotropic geometry. You may not have heard about it. This is a geometry with a degenerate metric. So instead of dx square plus dy square plus dz square, you cancel away the dz square. So you measure originally just in the top view, if you like. But then you need to define what is an isometric deformation, because with this, everything would be isometric, right? Any two surfaces, you just look at the top view. There is something, it fits actually, it's something like a Gauss curvature, right? Which one can define, and which popped up in your slides. You had z equals f of xy, and you had the determinant of the Hessian in the numerator of the Gauss curvature. This is the isotropic Gauss curvature. And then you define isometries so that they preserve the Gauss curvature. So here actually you put the theorema egregium in isotropic geometry as a defining element, right? And then you get non-trivial isometric deformations, you get discrete counterparts, and we could actually fully classify these mechanisms in isotropic geometry, planar quads, flexible in isotropic geometry. And then something very strange happened. You optimize towards Euclidean, the shape changes almost nothing, and they are flexible. So this is somehow still a bit mysterious, but yeah, this is a hard topic, this design of these mechanisms. Other work we did not do, not to speak about, you know, curved surfaces or so. And I'm afraid I will not do it because I'm already retired now, so I'm not so sure, right? I want to have my students to finish, and if I have an idea, I will tell my colleagues, but not work it out. Yeah. Okay. Oh, so yeah.
Wonderful tool. Thank you.
you.
So the question is, can you also define some calculus on this discrete geometry? So maybe a divergence operator,
yes,
gradient, so you can
this is an entire area, right? This is this discrete exterior calculus, and you can, yeah. It's partially you find a bit in this book by Bobenko and Suris, and you find a lot in the work of Mathieu Debrun, who used to be at Caltech. And he's now, I think, at École Polytechnique. So this is out there. Yeah.
Thank you.
Okay. Thank you, Helmut, again.
Okay, yeah. So if you're ready to start, the next talk is by Luciano Teresi from Università di Roma 3 on stress-free morphing.
Good afternoon. Thank you for the invitation. I'm very happy to stay here. And okay, it's working. So the first slide is this, say, quite famous paper by Turing. It dates back 52, and the title is Chemical Basis of Morphogenesis. So morphogenesis is in the title of this meeting. And in this paper, morpho is a pattern, essentially a chemical pattern. And so morphogenesis is the birth of chemical patterns that move along a medium. And in the introduction, Turing says that morphogenesis is a very difficult problem, and mechanics plays a fundamental role. But to keep things simple, he will not talk about mechanics at all, but only about the chemistry. And he solves a problem of something like a reaction. Equation. I don't know what's happening. And after so many years, also the talk that I've listened today, but other talks in other places, I can say that now after 70 years, we can say a lot of things about morphogenesis in the say true sense of the word. So the how form, how a shape can change, can arise, and so on. So my talk is split in three parts. So first parts, how it all began. The second parts, what is a stress-free morphing and how we tackle this problem. And the third part is some example of morphing design. And so how it all began, I was working on this problem. So looking at elasticity, where the input is not load, but the input are distortions. The famous example are thermal distortions. So you heat metal and it expands. There's no forces and it expands freely. It expands stress-free. And in the previous talk, Antonio Desimone showed us the bimetal strip. So the expansion would be free if the two pieces of metal were split together, but they are touched together. And because of that, when they expand, they bend and they accumulate stress. So the input is not loadings, but it is distortion. And then I start studying this kind of material, pneumatic elastomers, together with Antonio Desimone. So I have to thank him because I am in this, I'm working along this path, following this, it's very, very old, it's 2009. So this paper, we studied pneumatic elastomer, and we discovered that it's you can describe the behavior of this kind of matter using the notion of distortion. Here you see distortion is like a deformation, so it transforms a shape into another shape. Is a tensor, or a 3x3 matrix. And pneumatic distortion, because these are pneumatic liquid elastomers. So pneumatic liquids means that the volume element can change shape. Yeah, you have a sphere, then you change the temperature and you get an ellipsoid. And pneumatic because there is only one line. So here is the elongation. So this is a transverse isotropic deformation, one line and the orthogonal plane. And so this is a representation of this distortion. Is you have a parallel stretch along this line and an orthogonal stretch along this plane. So this tensor has an eigensystem, eigenvector, and the eigenspace is the plane. And this is what happens with the temperature. So high temperature, you see a ball, and then you decrease the temperature and you see an ellipsoid, long axis and the other short axis of the ellipsoid. And then we came up with this problem. I don't know why it's very... A Japanese group was fabricating this material, is rubber doped with liquid crystals, and they are able to orient the pneumatic direction. And when it's prepared, this material is swollen with a solvent, with a chemical solvent, but it is in the pneumatic state. Then you dry it, so you have a deswelling, and you observe a curved shape. Then you play with the temperature, and there is a temperature called flat temperature where it becomes flat. And then you increase the temperature and it bends the other way around. And these are three pictures, 1, 2, 3. So this is the flat state. And nematic distortion, but there are two different distortions. One is due to deswelling, because you remove the solvent. And the other one is due to temperature, because you can change the temperature. This one is irreversible. Once you dry the material, it remains dry. This is not, this is reversible. So you can change the temperature, rise and decrease, and you bend in one direction, the other direction. And so this Japanese group asked us, me and Antonio, we want a formula for the flat temperature. And I remember this very, very well. We were in SISSA. I was closed in a room. Antonio told me, we have to find this because it's very important to this collaboration. So we must find this formula. I said, okay, it's difficult. It's a mess. We have 2 days. It's, but we did it. So I was very happy about that. So this is the idea. Okay, you have the resultant the resultant distortion is the chain of two different distortion, deswelling and temperature. Moreover, because in the usual phase diagram you have the temperature is high when isotropic and low when is non-isotropic, nematic. You have to put this 1 to the -1. So deswell when it's nematic state, and then change the temperature and go back to the isotropic state. So this was the key idea, to split the total distortion in 3 pieces, and then the stretches have 3 pieces. And you can measure those 3 pieces. And then when it is flat when the distortion is a spherical tensor. So spherical tensor means that the parallel stretch must be equal to the perpendicular stretch. So the distortion is simply a constant times the identity. And so if you, here is the formula. This is the diswollen volume, so you can measure this scalar, how much the volume reduces when you take out the solvent. So the condition for spherical distortion, and so this is the formula for lambda flat. It's very simple because, okay, it's simple because you understand it. And this is the full diagram. So you prepare the specimen in the specimen is flat, so you can imagine that the volume element are sphere. Then you remove the solvent and you get an ellipsoid, and these are the 2 stretches. Then you increase the temperature, and those 2 stretches cross each other here at the same value. And at this point, this value of the temperature, you will observe a flat temperature. So it works very well. A bending in with, say, a concave and convex ellipsoid with this line, ellipsoid with that line, because red is smaller here, red is larger. So you can describe everything. Data fitting, can we also fit the wool heating and cooling? Yes. So the dots are the data, experimental data, and those 2 lines are the prediction of the model. So the model is working very well. It captures what's happening. And this paper has been published in 2010, so many years ago, and also he won a prize from the Liquid Crystal Society of Japan. And then what's next? Another question by this Japanese group. What about the stress? So is there stress inside this bar? Because the bar has a thickness
you can model it as a beam, but actually there is a thickness. This is a zoom of the nematic orientation when you fabricate the bar. And the hypothesis is that the nematic orientation, which is this double arrow, changes linearly along the thickness. And so the model is so good in predicting the shape, so we can solve an elasticity problem and compute the stress. And the answer is there is stress. Is always stressed, but at the flat state. And so, okay, yes, stress is different from zero. And then another question, but can we orient this nematic so that the stress is always zero? Any configuration is always zero. And we were not able to answer to this question. So this is a stress-free morphing, and I will say in a few minutes how to do it. You see that this cross-section is rectangular, it remains rectangular. So, and the cylinder now is a lot of grooves up and down, but okay, a few words about the notion of distortion. And now the second person important for this work is Sharon, who is here, because he was introduced the idea of target metric. So to assign a metric as a target to realize through a deformation. So I give you a target metric. Can you do that or not? In the realm of surfaces, so target metric means a first fundamental form as a target and the second fundamental form as a target. But here we are dealing with 3D objects, so we must solve this problem. And distortions is like a deformation. A deformation can do only one thing: take a volume element and deform it in another volume element. And deformation are used. Distortions are used in mechanics since many years. The thermal distortions, also plasticity are distortions. The plastic distortions are called also plastic strain or pre-strain. A lot of names. And they have a twofold nature, because to introduce the notion of distortion, you need also dynamics. You have to say something about forces, stresses, energy. It is not only kinematics, because what you say is that you deform a volume element, but this configuration is a ground state.
Mi piace. Grazie, sì. Posso avere anche una busta, per favore?
So yeah, I have a stack of 3 volume elements. I split them, and then I have a continuous field of distortion, 3 different values in 3 different points. And so these volume elements are distorted into this one. And now the problem is, can I glue together again? Usually the answer is not. You cannot glue together the distorted volume element. If you want to glue together, you have to add further strain. And so you end up with this diagram. Is the diagram used for this kind of in this model, in this theory? A body element, volume element. The body here is what you see, the actual shape of the volume element. You have a motion map. The gradient of the motion is the deformation, and you can draw this volume element to the gradient of the motion, using the gradient of the motion. But now you have another deformation, the distortion. So this is the ground state. It's not what you have, it's not your geometry, it's this one. You are plugging, say, a physical notion to matter. So this is a body manifold, but I want to say that this point X is not at ground state. So this volume element is not at ground state. This is the ground state. So the energy that you pay is for this deformation. And so we have the gradient of deformation, the distortions, and what is called the elastic deformation. And you can build a 3 metric tensor. And so this is the target metric, exactly the notion that Sharon was using. I want this metric as a target. This is the actual metric, is a gradient F transpose gradient of F. In elasticity, this tensor is, we use the letter C and is called right Cauchy green strain, but is the metric tensor of the manifold. And then if you put all this stuff together, you can build another metric, this one, which is called elastic metric. And in the elastic metric, you see you have both the actual metric, that is the metric tensor of the embedding of the configuration that you see, and the distortions. We use this tensor because you can demonstrate that to fulfill all the requests of elasticity, the energy, the elastic energy must be a function of this tensor, or its invariant, and so on. Anyway, I thank our man that helped me, because it took a huge effort to draw these slides. So now you can look at it. And the elastic energy must be a function of this one. So this is the right strain measure for the energy. So now the problem, so if you want to solve an elastic problem with distortion, you have to minimize an energy, which is a function of this one. And the elastic metric, inside the elastic metric, you have the actual metric and the target metric. And so our game is the following. I give you as input of the problem, as datum, the target metric, and the output is this one. You have to solve, to compute the strain everywhere, and that solve the problem. And so the question was stress-free. What do you want? You want a stress-free, how to get a stress-free configuration. C0, this target metric must be an Euclidean metric, so it must be realizable. So there must exist an embedding such that gradient of the embedding transpose is equal to the target metric. So you have to solve this equation, which is very difficult to solve. I using the standard cartoon for a system of equation. This equation is something like that. So you have 3 unknown, a differential operator that gives you 6 equations. So with those poor 3 unknowns, you must to solve 6 equations. So it's an overdeterminate problem. So in general, if I give you C0, it does not exist an embedding. And so the idea is to use this notion, the Riemannian curvature, because the Riemannian curvature is a test on a metric tensor. So you can evaluate the Riemannian curvature associated to a metric tensor. And there is this important theorem. If the Riemannian curvature is 0, then this metric tensor is compatible, is realizable. There exists an embedding, so you exist the immersion f such that so and so. And this formula, this theorem appears in this book. Is a book by Sierle in the first pages, but then he does not talk again about this important theorem. And also in this nice book of Alain Gorioli, it's Mathematics, Mechanics of Biological Growth. And so the idea is to use this theorem as a test on the target metric. So I have a target metric. Is it 0 or not? We are working in dimension 3. This tensor, the Riemannian curvature, has dimension 6. So this equation is six equations. Something about the Riemannian tensor, you find a lot of formula like that. So Riemannian tensor is the point of view is algebra, a lot of indices, or analysis, a lot of derivatives. So Christoffel symbol. So what is geometry? Anyway, this is a formula. We are using this formula because we want actually to compute the Riemann tensor associated to the metric. And so the Riemann tensor is a tensor belonging to this space. So what you can represent it like that. So you have a face element and another face element. So what it does, it takes a face and say the face on the base manifold and give you another face. And there are also all these symmetries. And you can represent it visually with this matrix, 3x3 matrix, 3 block matrices with 0 is a skew. So this is minus this one, and each of these one is a skew matrix because each of these matrix actually is a rotation. So it's not a rotation, but is the skew symmetry matrix associated to an infinitesimal rotation. And so 0 on the diagonal, antisymmetric. So if you count, you have 1, 2, 3, 4, 5, 6 independent components that are shown here in red. And so using this tool, we were able to answer to the question about the nematic orientation. Okay, this is the nematic distortion. This is the target metric. So it's simply the transpose of F0 times F0. This is the target metric. And now the unknown is the orientation of this director, N. And what happens if you put this metric tensor here? You compute the Riemann tensor. It's a mess, but in this case, 5 components are 0. You have only 1 component different from 0, which is this equation. So you have a differential equation. It is nonlinear because alpha is the angle of the orientation. Alpha prime square, sinus of 2 alpha, second derivative of alpha. But this equation has a very simple solution, which is this one. So if you orient the nematic line along the thickness, along the Z, with this formula, using this formula, you will have a stress-free configuration for any temperature. And moreover, the linear orientation is this line. That formula is the red line. So it's very similar to the linear orientation that was supposed to be. You cannot measure it, but you imagine that top is horizontal, bottom is vertical, and so it varies linearly in the thickness. And this is a bending, but we call it a nematic bending because it's not the classical bending where you, at the bottom, you shorten the fibers, at the top, you extend the fibers. No, you are doing something like that. So is a sampling of the distortion, compatible distortions, and you can bend like that. And you see what happens at this side. And all these configurations are stress-free. So I change the temperature and I bend without inducing stress. And then after that, we were very happy. So we can solve a problem. I was not so confident because to compute the Riemann tensor associated to a metric, it's something that if you do it by hand, maybe 1 week, I don't know, I give you a matrix full of 1 day. But if you want to understand something, you must, okay, it's, for me was really a surprise. And then C, explore different distortion instead of a nematic distortion, which is transverse isotropic, so one line and one plane, and orthotropic distortions. So 3 different eigenvectors. So I can change the stretch in 3 different directions for a simple shape, for a cylinder, and not any distortion. Put the variable only in some places. So try build this distortion looking at the symmetry of the body. The body is a cylinder, there is an axis, and so this was the idea. So this is an ansatz, so start from here. And also an ansatz for the immersion. How is the immersion? So here we have some parameter. I don't know this function. I don't know this function. I don't know this function. And again, we put this one in the Riemann tensor, and we find the solution. And these are the compatible distortions. So what you can do without storing a large elastic energy, the green, so the gray box is the base manifold, and the colored one is the distorted, so manifold, volume element. So this is the distorted volume element. So you can elongate like that, you can change the shape like that, so many different ways. And so you have a full library of stress-free shaping of a thick object. This cut is to show what happens inside. So you can have a torsion, or you change. So a lot of things. Now the third part of my talk is, okay, now we are able to solve this problem, but can we design a morphing, a more general morphing? I want to morph this body into this shape. How to do it? And our idea was, okay, we have to use this tool, but the important thing is that you need an ansatz for the target shape. If you are able to build this equation by hand, so I want to transform a block in a tree, and I can write all the equation x, y, z of my block to x, y, z of the tree, then I can do everything. So ansatz, compute a target metric for this ansatz, put it into the Riemann curvature, and then try to solve this equation. Maybe if you are lucky enough, instead of 6 equations, you have 3, you have 1, you have 1 equation, 2 equations that are simple to solve. And how to build these ansatz? our idea was the following: start with the curve. On a curve, I have a frame, and then upon this frame, I build a surface, and then I extrude the surface along another direction, here, and I get a volume. So start with a curve. Then the curve becomes a surface, the surface becomes a volume, but I have an explicit formula for this, say, volume. And I can put in this formula some parameters, so I can generate a lot of volumes. For example, a thick helix around the cylinder, and with my parameters control the pitch, and so the torsion, a lot of things. And so I have this a library of this function. And so we start playing with this function. This is a distortion. It's very simple distortion. This is the metric and the target metric. And for free, all the 6 components are 0. This is the classical bending. So the bending where elongate on top and contract at the bottom. And this is the image of the bending. And this bending is can be as large as you like. So is at the end here, volume element here will collapse to a line which is not feasible, but okay, it's any configuration is stress free, and also here. And you see, you may see these blocks as volume elements, as a sampling of volume elements. And then what happens if you put a function here, f of x? So if something along the axis of the beam is changing, again, you can put here any function, whatever you like, you get always 0. And so you can do, for example, a curling. So the bending is increasing, so the radius of curvature here is smaller than here. And so it rolls. Or you can morph like that. Yeah, I have a curvature concave and convex. Okay, this was easy. And now another kind of bending using again the distortions, transverse isotropic distortion, similar to the nematic one, but not exactly the nematic one. This is the distortion. This is the target metric. Here you have a function of z squared, and now you put this target metric, the Riemann tensor, only one trivial non-component, and this is the differential equation that you have to solve. You can solve it very easily, solution. And so this is the embedding. And so now we have a library with 3 different bendings, with 3 different, say, distortions. All of them are stress-free. And you see the shapes of the volume element are very different. Design a torsion. I want a torsion. Again, starting from the ansatz, so this is a target metric that we want to test, a target distortion, a target metric. We solve, and with this function, the Riemann curvature is 0, and so is stress-free. And here you see the volume element. The volume element deformed with that distortion. The input is only that one. So it's a sequence of increasing. There is one parameter, is this one, is increasing from 0 to 5 pi. So it rotates 5 pi with respect to the other section. Ribbon. Now we want to design to generate ribbon. Target metric. And now it happens that 3 components of Riemann are 0, 3 components are the same, and this is the differential equation that you have to solve. And this is a solution of the differential equation. And again, you have a parameter. For example, this R is a parameter. And so you can generate ribbon. And you can also design the morphing such that the ribbon becomes a tube. So I have a flat bar, and I want a ribbon that generates a tube. This is not the case. So this is during the morphing at the final configuration, this is a tube, and now you will see it becomes a tube. It will stop. Okay, it's a tube. And so I can. This might be an interesting example for biological devices that want to make something like a tube, starting with a flat piece of tissue, for example. How the cell should grow or should, say, distort to go from here to here, but without increasing the elastic energy. So it's for free from the elastic point of view. The power input is only used to generate distortion, but not to increase elastic energy. And this is another example. We also tested another geometry for nematic elastomer. Nematic elastomer with a chiral geometry means that the nematic lines are not vertical or in this plane, but are horizontal. And what you do is on top you have this line, then when you go down you rotate, and at the bottom you have another direction, always horizontal. And this is what happens. And with this arrangement, so with this field of nematic distortion, you always have stress. So this configuration is never stress-free. Okay, now we can play with those two, say, mode of deformation, bending and torsion. So this is a Möbius. It's not a Möbius strip, but it is a Möbius bar, because you have a thickness, and the thickness can be very large as you like. So it's so I bend and I twist, and so I have this kind of. Last example, we want to avert a solid cylinder. So now the color map is inside outside. So red is outside, and now red is inside. And how to do it? So again, try to build a map with an ansatz, and the idea is this one, each cross section must rotate along this normal by an angle. And so I have an axis of rotation, an angle of rotation. I can build the skew tensor associated with the rotation. Then I use the Euler-Rodriguez formula. So rotation exponential of alpha W. So this is the rotation, and now alpha is the parameter, and this is a field that I can assign, and this field is a field like that. So a vector tangent to this line. And it works, you put this deformation into, this is not a rigid motion because the rotation is different section by section. And here you see the cross section that rotates, they remain rectangle. 4 rectangles that are rotating, and now, okay, and here you see the volume elements. You see the small, and now they grow again. And so now the red is outside and the blue is inside. And the cylinder here is very thick, but can be also very thin. So you can go to the limit of a surface. So this is a cylindrical, say, surface. Actually, this is a volume. The thickness is not 0, but we can do the same. We can play the same game. It does not closes the hole. And you see these cross section are rotating. And here you see what happens to the volume elements. Okay, this is my last slide. Now, what's next? What we want to do is to put some noise in this compatible distortion, so that to obtain something bistable. So it's stress-free until a given value of the parameters, then it accumulates stress, and then it jump above a threshold and becomes again stress-free, or almost stress-free, but it's our future. So I stop here. Thank you for the attention.
Thank you very much. Thank you also for reminding me of the good old times. Actually, I remember the scene that you were describing. So the Japanese guy is a famous colleague. His name is Kenji Urayama. And I remember the scene. I don't remember the words, but I recognized myself in those words. But I have to specify that it's not because I recognize myself as with a whip and
sure.
saying, but it's an important. So I wanted to say this because so this was a collaboration with a distinguished guy, and we had to prove ourselves basically. So the idea is that so I recognize myself because I was taught that if you want to collaborate with someone, you have to solve the problem of interest to the other person, right? So you cannot say, trust me because I can solve this and that. I mean, to prove yourself. And so that was the spirit. The spirit was that we had these 2 days. I mean, this guy was with us from Japan. And so we asked him, what you really want to know? And he said, this. And then I told Luciano, that's what we have to do. So anyway, so questions, comments?
Yeah, so something which you said at the end I found very intriguing. So how close are you to sort of designing bistable things? I mean, Antonia explained very nicely that this would make really nice applications.
Okay, I have this micro. So for this 3D morphing, we are very far because when we can solve this problem with say a finite element method, so we can see what happens. And for example, we can we can follow the Riemann curvature, see which components are different from zero, where are different from zero, and how much. So this is something that we can do just to have a clue of how large is the incompatibility, but not about the effect of the incompatibility. For the surfaces, the talk of Antonio Desimone in this morning, the one about the, how do you call it? The
curved crease?
The curved crease,
Curved
yes.
crease origami.
Maybe we are more close to that.
Yeah.
This example that he showed this morning was actually bistable.
Yeah, so that is a bistable thing, which is done in 3D, but it's a thin geometry. So, I mean, of course, the whole, I guess, the whole purpose of your thing is what to do away from the usual situation in which we actually morph things because we know, I mean, it works, and how to do this in thick geometries, right? So you have to do, and actually maybe again, if I remember correctly on the Urayama thing, you saw that the profile of the linear profile and the cosine profile that Luciano came up. So you know, these things become different only when there is a lot of thickness. I mean, the thickness is large, but when it's very thin, you know, I mean, on the midline, whether it's linear or the linear tangent. And for example, in my recollection, we didn't manage to win Urayama completely because he could predict the radius of curvature, even though it's a stressed configuration, he could fit very well the radius of curvature of the ribbons that he was producing without solving the elasticity problem. He was using the target metric, okay? And so I think we never really managed to convince him that there was a need to solve for the elastic thing. But just because his strips were thin, I think. So, you know, if we knew this and we had managed to convince him to build very thick samples, maybe that would have been the way to convince him. So.
Another, if I may add a comment, another direction could be to link this work to the original paper by Turing. That is, I have a chemical pattern moving around in a medium, and now if I link the value of a chemical substance to the distortion, so the growth is feeling what's happening, and so maybe I can morph something with a couplet problem.
So it's not a question, it's a comment related to this discussion. When communicating it to people that are not familiar with the details, I think an important and non-intuitive property of such structures that you design is if you want to actuate them many, many, many times. So normally people think about flexible thing as passive one, and you can bend them and relax and bend again, but they fatigue because they are strained. And these structures are not strained at all.
Yes.
So the erodium on that Antonio showed, they can be actuated on and off thousands of times with no fatigue. And I think this is an important property to communicate.
Yes. Further questions, comments? Okay, so let's thank Luciano again. Thank you very much. So this is the last talk of the afternoon. So we'll have the coffee break after the talk. I mean, the stuff is there, coffee is there. And okay, so the next speaker is Miles Simon. And the title of the talk is Integral Curvature Estimates for Ricci Flows with Bounded LP Scalar Curvature.
Yeah, thanks, Antonio. And thanks to all the organizers for inviting me here. This has been a great conference. I'm really enjoying the talks, and I like the fact that there's lots of new input coming. Yeah, I'm really, really interested in what's happening. So let's see, here's the title of the talk is, as you see, Integral Curvature Estimates for Ricci Flow. It's about Ricci flow. So before I get into the estimates and you know what's going on in this particular talk, what the LP scalar curvature bound estimates are on about. I just want to give maybe a brief introduction to Ricci flow, because I think there are some people who are not always working in Ricci flow here. So let's just have a quick look at what Ricci flow is. So Ricci flow is concerned with manifolds, any dimension you like, finite dimensional things at the moment. And you're interested in finding solutions to this equation here, i.e. you're looking for smooth families of Riemannian metrics. So you're looking for a time parameter, a family of metrics parameterized by time. So we're interested in finding, as I said, these metrics which are parameterized by time, and they solve this equation here. So Rich is always the Ricci curvature. And so sometimes, in this here, I've just said it's just a solution to this equation. So sometimes you're starting with an initial manifold, mg0. That's your starting manifold. So think about it as being closed for the moment, although it doesn't have to be closed. And you're looking for these g of t's which solve this equation and have, if we call this one g at little z 0, you're looking for a solution of the equation given by this formula, starting from this initial Riemannian metric. Okay, so the Ricci curvature, well, we heard about various curvatures in the previous talks and other talks. So the Ricci curvature is like a sum of sectional curvatures. But if you're coming from analysis, then maybe you just want to see some derivatives and some formula. So locally, we can always describe the Riemannian metric using coordinates. So if you've got a manifold, maybe it's got some topology, and then you have a little, you can always find around any point you like, you can find some coordinates so that it's just diffeomorphic to a ball of, say, radius 1. You can stretch it out. And then you have this Riemannian metric, which is defined at each point in the tangent space up here. And it's giving you a scalar product at each point here. So if this is a P, then g of t at pt is just a scalar product. That's all it is. And then, of course, you can write it locally, just breaking it down into its various parts. So you can just write down a bunch of functions, which I call gi, j, x, t, and everyone does in Ricci flow. And they're just given by g at the point upstairs. So if here's your x here, and here's your y here, and x, y is mapping down onto x, then g upstairs evaluated at the coordinate points, coordinate vectors at that point there, will give you a bunch of functions. So that's a j. And these functions, of course, define your scalar product. So you can just think about, you have this system of matrices. This is an n times n matrix where I and j are in 1 up to n. Or you can just think about them as a bunch of functions. And then you can look at the evolution of each of these functions down below. And locally, this is what it looks like. So it's nice if you, just to see what's going on for the evolution of the Ricci flow, you're evolving these functions which define the scalar curvature at each different point according to this equation here. So you see it almost looks parabolic, right? There's second derivatives here. This is an inverse of the metric. So it's an inverse of the matrix given by g. Here are lower order terms. This means, by the way, that's the second derivative in the direction h and I. This is just the first derivative in the direction h here. So there's a certain summation going on. As soon as I have an hi above and an hi below, then I'm summing over those. So you can see j and k are fixed, and you get these formulas. And you can write it actually down explicitly. I didn't write all the terms down, but you can see you've got this equation. So you get some sort of feeling for what the Ricci flow is doing. It's a PDE. It's almost parabolic. This is not quite parabolic. If you work out the symbol, it has some zero eigen values, so you have to do some more work to show existence and regularity of these things, but there's various ways of doing it. You can either do the Nash-Moser inverse function theory method, or you can modify the equation to make it parabolic and solve the problem. So that's what the Ricci flow looks like. Oh, well, that's what the equation looks like. So let's have a look now at maybe some examples. Before we look at some examples, let's just go quickly. The main existence theorem is here. I said you can get existence. You start off with an initial manifold which is complete, has bounded curvature. So the supremum of the curvature is bounded. Then you can always find a solution, and you can find a maximal solution. That means you find your solution, it lives up to a time big T. This big T could be infinite, and then it just means it lives forever. Or if this big T is less than infinity, then you know, this was proved by Hamilton, that the curvature is blowing up as time goes to this final time here, i.e. the curvature is going to infinity. Yeah, so this is called a maximal solution. In fact, she examined this equation shortly after Hamilton's first paper and showed you can get the same result even on a non-compact space. This still works. So that's nice to know. We've always got existence, and everything's smooth right up to the time that the solution fails to exist, if it fails to exist. So a simple example is given by the sphere. So just taking n dimensions here, you can take an n-dimensional sphere with sectional curvature. Gamma is the standard metric. That means sectional curvature is 1 everywhere. And you can then look at what might be the solution, or what is the solution. It's a pretty simple exercise. You can just work it out exactly. G of t is given by this formula here, 1 minus 2 times n minus 1t times gamma. So you just scale your metric on the sphere. Okay, so you see, well, this is good. We see for the first time that there's some problem at a certain time, because this shrinks down to nothing at the time big T is equal to 1 on 2n minus 1. And so here I just did a quick calculation to show that this really is the solution. If you do ddt of it, you get this. But that's actually per definition, because it's sectional curvature 1 everywhere, it's exactly, this quantity is exactly minus 2 times Ricci of gamma. And now, remembering that Ricci curvature, if you looked at the formula I wrote on the first page, you'll see that this is actually Ricci curvature as a tensor is scale invariant. That means I can scale it and it doesn't change. So you see, now I've got g of t in here again, so we found a solution. And Hamilton result also says it's the unique solution. This is how he formulated his theorems. In the non-compact case, there's also a uniqueness result, but that's in the class of solutions which are bounded. There's possibly other things that can go wrong there, but let's just stay in the closed case. It's the solution. Okay, so the solution becomes singular at this special time here. So here we go. We start off at time 0, and then you start flowing down. It's supposed to be nicely scaling down, and then poof, it disappears or explodes at this time, right? So that's a nice example to have in mind. What other things can happen? By the way, this can happen in any dimension. So apart from 1, in 1 there's no curvature. So n is bigger than or equal to 2 in this here. There's no Riemannian curvature. You can do rotationally symmetric data. So here I'm looking at, let's just stay with r times s2. You can put a metric on it, where I put just a standard metric on the r direction, and in the other direction I warp the s2. So gamma is once again the standard metric on s2, which has sectional curvature 1, and you warp it as you move along the r, so you're changing it. And I took this function here, a squared is a constant less than 1, maybe less than a half is even better to make sure there's a bit of room. And you then warp your metric according to this formula. And what happens here is something interesting. The Ricci, the metric becomes singular at some time. This is what I showed at this time here, and later I didn't write this down here, but Angela and Knopf looked at similar methods for compact things. And then you can show that this thing becomes singular, but not everywhere. So it's better just to look at the picture. So here, this one I closed up, so you can, going back, here it's on the whole of R times S2, but you can just close it up so that it's a sphere, or a part of a sphere on the end here. And here's the warp product structure. And if you choose, it's steep enough here, and there's enough region here, then what happens is it starts, this part has curvature, it's a two-dimensional sphere, so it starts crushing down. The other's going slower. Remember how the sphere was moving down? And okay, there's curvature in this direction, but everything's worked out nicely. So in fact, things really do get to this picture I've drawn here, that this one crushes down a lot long before these ones here disappear. So they're going down, and in here you get this singularity. And okay, so one thing to note here is that the way I've drawn the picture, it looks like the diameter there is finite, but in fact this is, in certain situations you can show it's finite, but in this general situation it's not always clear that this is finite here. Yeah. So it's a good picture, but you have to be a little bit careful. And one other important thing to notice by these two examples that we've seen here is that we can really see what's happening near the singularity. So we can see the topology. Okay, I don't just see the topology, you can actually, this is results of Perelman and Hamilton, I'll mention this. You can see what's happening to the region where it's becoming singular. If you blew this up, you scaled it, then you will see this nice sort of cylinder. So if you imagine just before the region becomes singular, you can blow it up, so you scale. So this middle part has maybe sectional curvature 1, and then you sort of see this region which is almost like a cylinder. It's starting to open up slowly, but it's getting longer and longer. So two things, you see the geometry of the singularity as I've drawn it, you understand what it looks like, but not just that, you see the topology. So you can say, you might want, for example, you can imagine the procedure, and this is what Hamilton's surgery idea was, is that you just before you get singular, you do a cut. So you cut off there on both sides. And if you know enough about how it's looking, so you cut it off and then you patch it on with a little cap. So this is just before it becomes singular. Why just before it becomes singular? Because then you know more and more about this singular region. You cap it off and then let it flow again. Okay, so when you do that, the point I'm just trying to make and stress here is that when you're doing this, you really know what the topology looks like when you're getting down to this singular point. So you can keep track of what you took away, and in the end, you can try and reconstruct the topology of the whole thing. Okay, so that's useful fact, is that we really see what these sort of singularities look like. Here's another nice example. Angel and Knopf and Wu and Gu and Su looked at this after. So now you've got this sort of rotationally symmetric thing again, but now your neck is quite small, but here it's not too big. And what you have to choose the ratios carefully so that this one's crushing down, this one's crushing down, but it starts to suck in at the same time. And in the end, you get this sort of, this whole thing crushes down, and what you're just left with is this little part here. Once again, I draw it as if it has a finite diameter. This is not actually completely understood. And Perelman called these things horns. So they kind of look like horns, right? And you can show that these examples are explicit in the rotationally symmetric case. In the general case, you can show they happen after rescaling. You can understand the situation. Okay, so they're good examples to have in mind in the three-dimensional case, because there what we see is these examples that I showed, you always know just before you get singular what the topology is like. Here we have to cut. For example, here you might want to cut and patch on a bit and let it flow again, and then the bit you took off, you know what it looks like. You know about the topology of it. Okay, so those are good examples to keep in mind, and in fact, in the three-dimensional case, that's roughly all that happens, which is quite remarkable. Up to topological considerations, these are the sort of singularities that are really happening, and this was the whole kind of great results of Perelman and lots of other people involved, was to really understand these singularities. Okay, So this is still a very vibrant research area, is trying to understand singularities, but now in higher dimensions. So in 3 dimensions, the pictures I showed show roughly what's happening up to topological considerations. And Perelman proved this. He really gave a great explanation of how these singularities look like. And this has been improved, by the way, in the future now by many people. I'm not going to start listing people, but lots of people have improved the understanding. And this was used, this sort of procedure that I mentioned, so you might want to cut and then continue to flow, was used to prove that the Poincare conjecture and Thurston's conjecture are correct. And okay, so that's sort of 3 dimensions is very good. There's still, by the way, open problems there, but it still was a lot was done, and it's been very, very successful in this area. Now, what about higher dimensions? Well, the next dimension that people are working on at the moment is 4 dimensions. There's been lots of progress there also, and but there's still lots of things that are not understood there. So we're just going to look in this talk at one sort of setting to try and see what sort of singularities could happen in 4 dimensions. And as a sort of, you know, in order to kind of hope to contribute to the picture of understanding what singularities can occur in higher dimensions. And there, the situation is, of course, quite different. Of course, you can always have an R times a 3-dimensional thing, so you could always have the 3-dimensional examples I had before. But of course, there are now maybe new sorts of singularities. And that's roughly, well, that's related to what I'm going to explain now. Okay, so let me see. We have to get the setting set up, so there's a lot of information here. Let's just go through the most important part. So we're looking in 4 dimensions now. Well, actually, one of the main results is in all dimensions, but if you want to stick to one of the applications, you can think of 4 dimensions, but it works in all dimensions, the first part. And you have a solution to Ricci flow, and it's becoming maybe singular at this big time t. And there are 2 settings we look at. One is, like I said, general dimensions, but there I need to restrict to it being a Kähler solution. So this has a sort of complex structure behind it, and the metric has a complex structure which is preserved. And and also it's closed. The other situation is just 4 dimensions, M being a 4-dimensional solution. And what we're interested in is these sort of regions. We also want to kind of localize the situation. So we saw in the example of the neck pinching that you can actually have local regions where something becomes singular, but the whole manifold might not become singular. The first example, everything became singular. In the other example of the neck pinching, you saw just some little region become singular, maybe just one sphere collapse, maybe. And so it's interesting to sort of focus on regions and to try and understand what's happening in regions. There could be a good region where nothing's happening and a region where something's becoming singular. So we're focusing on a region. The manifold is doing something, we don't know what, outside of N. So kind of think of, here's your manifold. And you've got some region inside. So this is M, the whole thing. And now we just look at a region inside of it. So this is our N inside here. And you've got some boundary, of course. Here there are 2 parts of the boundary. And N's going to be compact. And you want to assume that on the boundary for your solution also that everything's controlled on the boundary. So this is like if you go back to the picture of the pinching, away from the neck region, everything's nicely controlled. So you just assume you have this control there. Perelman's pseudo-locality theorem will show you that if you have enough control at time 0 and big T, the possible blow-up time is not too big, that in fact this control on the regularity will remain true there. So it's not, in many settings, it's a sensible sort of assumption to have. Okay, but of course, it depends on the situation you're looking at, but we want to stick to this situation that around here, so I call this region omega, maybe draw it like this, is omega near the small neighborhood of the boundary. You want to assume that on omega, that your metric is evolving nicely. So the curvatures are bounded there, right up to a potential blow-up time. This potential blow-up time, big T, is finite, and nothing's going wrong in this region here. What's happening outside, you don't know, and you're not interested because you're focusing on this region here. So the question is, can there be singularities in here if we make certain extra assumptions on this area here? And okay, so what are the assumptions that we make? Yes. Well, canonical, I don't know, but if, let's say your time big T here, let's assume it was 1, okay, or 2, the time where you're interested in goes up to 2, and let's assume that you knew at time 0 that you have your radius of this omega, you've got lots of balls which cover it, let's say they've got a very big radius, I'll just say C of n, which sits in omega for all p's here on the boundary. Every BCN is sitting in omega on the boundary. And on this BCN, let's say you're almost Euclidean. So you have almost Euclidean structure. Then Perelman's pseudolocality theorem will show that in a slightly smaller region, that right up to this time 2, nothing can go wrong there. So it's an example of a condition you might want to have that you're considering there, that where something can go wrong. There are other situations, but canonical, I think, is too much to ask for. It's more about, we know, for example, if you go back to the neck pinching, I had these big spheres. There I know from Perelman's pseudo-locality theorem that nothing can go wrong on those big, it can't collapse down the curvature, it can't become very large for a controlled time. So up to time 2, yeah. The points, so this region omega is a topological region. So this is the balls at time 0. So I say, if I know at time 0, the metric's controlled there, then I know at later times it's also controlled there. So I don't need to worry about this evolving in time, this region. I can show, if you go a bit further in using Perelman's pseudolocality, that's controlled. Yeah. Yes. Yeah. There are certainly other ways where you can have this control, but the question is, it's all about trying to understand, assuming you have a nice boundary region where things are controlled, what can happen on the interior? Right. In sort of leaning upon this example with the neck pinching. Okay, so let's see. You can here. This is not too important. I've just said that after scaling, you can always assume that T, this blow-up time, is bigger than 2, and that curvatures are less than or equal to 1 up to a certain order. This is not too important. What's important is just assume that everything's completely regular on the boundary here, that you've got lots of control on curvature and so on, and we're interested in the region in the interior. Okay, so yeah, this slide's a little bit technical. Let's go through it. So here's the basic integral estimate. I already forgot to mention this is joint work with Jiaobai Liu, who's in Nanjing. And right, so we're in this setup I just mentioned over here, and you look at the Ricci flow. Now here, we show that certain integral estimates hold without any other assumptions. Okay, so this one here is always true for the Ricci flow. Okay, so that's why I call it the basic integral estimate, because it gives you information on any Ricci flow that the setting we're looking at has to be 4-dimensional or scalar, then you always get this, assuming you have this nice control on the boundary. If you don't like this control on the boundary, you can forget it and just assume that M is closed and that N is, empty. That's also fine. So this works also in the setting that the manifold is a closed manifold. Yeah. Okay, so what's the estimate? Well, it shows you somehow or other they're sort of weighted integral estimates. It tells you can get some sort of control on the integral of the Ricci squared, weighted. This is the scalar curvature, so I always use 1R for the scalar curvature and Ricci for the full curvature, and Ricci for the Ricci curvature, and Riem to represent the full curvature tensor. Then it's showing you can get control of a weighted Ricci curvature in terms of, so these are the terms you want to get under control. They're both positive, non-negative terms. You can control it using an earlier time. So if you like, you can take this R to be 0, right? This would be the metric at time 0 here. They're very general, the estimates, but just as a starting point, it's probably good to assume that little r is equal to 0. So this is the metric at time 0. So everything is controlled then too through compactness. And then so here's the terms you want to get under control, some integral estimates. And here's the thing that you're bounding them by. The scalar curvature to the power of 2 plus some small power. So this alpha is between 0 and 100. It's always good to think about alpha being small. So this is the sort of term that we consider. You try and make alpha a small. It's nice to choose small alphas because then this term is not that, the power is not that large. You have to pay for it in this term here. So that's the payoff, but nevertheless, it's about an estimate for small alpha. Another thing maybe to consider is take S is equal to V, then this term disappears. Okay, then you just have integral Ricci squared, so you have a real bound on integral Ricci squared coming from this scalar curvature bound here. And an interesting feature of this also is you get this space-time integral of higher powers, but the weighting there is also higher. So it's useful, this term here, but it's still maybe not. First, you might think it's really good because there's a power of 4 there, but in fact, you have to worry because here there's a scalar curvature and you've got a power of 2 there. So it's useful and it's used in the things our applications, but as I said, you should take into account that there's a power of 2 there. Okay, and then you can sort of play around with this integral here, and I gave you some ideas about how to do it. I said take V, S is equal to V, and then you can actually get a bound on Riem squared. So the full curvature tensor squared is bounded by, once again, what are you controlling it by? This term here. So this is perhaps the best one to look at first if you're not used to all these things. The rest of them are just constants. It's not to worry about. The hope is they'll be useful when R and S are in close to one another, but at the moment, it's best to consider R is equal to 0 and little s is equal to going up to this time V, which is less than t. And then using this, you can actually get this kind of pretty clear estimate. The full curvature tensor squared is less than or equal to this estimate here. Okay, so that's probably the easiest one to understand because it's then completely clear. So just a reminder, up until now, this is for dimension n equal to 4, both is correct. For higher n, you need scalar. Okay, so we'll see why that's the case in a moment. And if n is equal to 4, this will come, I think, for people who are working in geometric evolution equations as no surprise because it's scale invariant. That means if I scale the metric by a constant, this quantity here doesn't change. Okay, so that's why it's not too much of a surprise that this comes up in n is equal to 4. Why it comes up in the scalar setting, there it's not scalar invariant for higher n. We'll come to that. So, yes. Yeah. Mm-hmm. Okay, so first of all, this is something which is integrable, as you pointed out. That's very useful. That's what we use. And yeah, we had to bump up the alphas above, so it's not the same as, say, alpha or something like that, or maybe 2 alpha. This can probably be improved to a lower alpha. But just in the estimates that we proved, using various Holder and Young's estimates, or
in 1 unit of time for 2 units of length.
right. One will have to see if one can improve this to another power of alpha. It's possible. Yeah, I can't answer the question at the moment. Yeah, we'll see where it comes up at in any case. Yeah. Okay, so those are the estimates. And like I said, for the first, it's true always in n is equal to 4 and also for Kayla. Okay, so here's, I guess, going back to it, I'm just making some obvious comments. If you assume this integral is bounded, then you've got integral Riem squared is bounded. Okay, and that's a very useful estimate. I mean, as soon as you have integral of the Riemann to the power of 2 being bounded, the sorts of singularities which you're going to expect are orbifold type singularities. Okay, and it's giving you a lot of control on the curvature. And so that's the first comment. Okay, and the second comment was I sort of explained how to get this the Riem squared estimate. You essentially choose S is equal to V and R is equal to 0, and then you have this estimate here. So you even get a bit more. I didn't put that one in the second one, I think, but you get a bit more. So you don't just get integral Riem squared being bounded, you get this. Okay, so that's the idea. Now, just trying to remember some other point I wanted to make. Oh yeah, there's a simple case where you get this here. So as Felix pointed out, this is not too bad. It's 1 minus alpha, so you can actually integrate that if that term wasn't there. And in fact, that's what the next comment is. Assuming you knew that integral n of scalar curvature to the 2 plus 12 alpha is bounded uniformly up to the possible singular time, then this is integrable then in time, so you get just some constant. So then you would actually get this estimate, which is being claimed here. Right. So, right, those are the comments. Okay, so that's a nice start. You've got these bounds on integral Riem squared, and this may be very useful in dimension n is equal to 4. Hopefully you can show the singularities. But there's, you can show their orbifold type singularities. But an important feature that's missing is always in these understanding singular regions or understanding singularities, if you really want to have nice control on the regions, like I want an orbifold which is not becoming too steep or something, then you would like to have control on collapsing and non-collapsing. Okay, I'll explain what that means. First of all, the good news is that Bamler showed already in a paper which I've mentioned here, that you always get these non-inflating type estimates, and I'll come to what they are on the next page. Okay, so let's just have a look. So now we're going to stay in the dimension, it's closed, and it's once again in the basic setting, and I'm just assuming the information I said before. If you have this bounded uniformly, then I've written down these big integral estimates in a different way. So this one's just now integral Riem squared bounded. 2, this one doesn't immediately, it follows after a bit of work with the previous inequalities. There's a bit of work to be done here. And this one is not, this one, the scaling is improved. Okay, so here you'll see you've got alpha to the 3, so alpha is very small. And here you just have some alpha. So the power here is for small alpha, of course, a lot smaller than alpha on 16. That's very useful. So here's a typo. This should be n on 2. And yeah, so if you assume in any dimension that your scalar curvature now to the power of n on 2 is bounded, then you get this extra, what I call a non-collapsing estimate. So the volume of any ball of radius r is bigger than or equal to sigma r to the power of n. And the non-inflating one is, hopefully on the next page, here it is, it's bounded from above too. So the Euclidean ratio of volume is bounded here. So volume divided by r to the n is less than or equal to sigma 1, and volume of a ball of radius r divided by r to the n is bigger than sigma 0. So we get all this information. Just go back a moment. We've got now, this is bounded, but in a very nice way, because it's not a scale invariant inequality, it's a better inequality, it goes the right way. And we get these nice estimates using Bamler's non-inflating estimate and our non-collapsing estimate, which hold in this setting. And here I just make the point that this estimate I wrote down before is actually not, it breaks the scale in a good way. So if you scale your solutions, as I've done here for some big constant b, this would be the correct scaling for a Ricci flow solution, then let's write down what happens for the new solution, looking at the quantity I wrote down before. You get the same thing, but you get this constant coming in here, and that goes, as b goes to infinity, goes to 0. So it gets even better. So at a scaled level, this quantity is going to 0. That's very, very important for the analysis that we look at later. Okay, so these are the main estimates and some of the main points behind the estimates. So I'm just going to give some ideas behind the proof, because maybe there's one more. I think I'll write down one more statement here. So let's stay now in the four-dimensional case and assume this condition. Now we're going to assume that on the whole manifold that your integral of the scalar curvature is bounded, 2 plus sigma, sigma is bigger than 0. Then as you're going up to the possible singular time, you're getting finitely many orbifold singularities. Okay, so I'm just going to draw a picture of what can happen here. So here's our evolving manifold. Of course, I'm just drawing pictures. It's not embedded anywhere. So these are intrinsic spaces with topology. And you've got some region, maybe we're assuming now on the whole thing that the integral of the scalar curvature to the 2 plus alpha is bounded. Then what could be happening is the following. You might have some sort of cone region here over S3s, but actually S3 is divided out by groups. So here's a little cone region. Maybe you need one more there. Inside here, there's some topology. So I've just written a little question mark there. You don't know exactly what it looks like. And as you go up to the possible singular time, these kind of topology is crunching down and disappearing. So there's no topology in the limit. It's really a cone, a Euclidean cone, over these spheres, these S3s. So you have some sort of cone here. And maybe there was another point here where it happened. These presumably different S3 divided by groups. So you have these different sort of orbifold type singularities. And then once you're but everywhere else, so on this part here, the curvature is bounded and the manifold is completely, the Riemannian metric completely controlled. But this, of course, is no longer a manifold, right? Because here you have a cone over something which is not an S3, it's an S3 divided by H, where H and gamma are non-trivial. I didn't write this down, but they're non-trivial groups. It's not the identity. That's important. In this setting, if you get singularities of this type, then it has to be a non-trivial singularity. So it can't just be with an S3 there. That can't happen. And everywhere else, everything's smooth. So either nothing happens and you get a smooth limit and you can continue the flow, or there's these possible sort of cone-like singularities occurring. And if these cone singularities are occurring, the good news is they're so well controlled that you can actually now continue the Ricci flow past this time, but not using Ricci flow, you have to use the orbifold Ricci flow. Okay, so that means in an orbifold Ricci flow, it will continue, do the Ricci flow here in the smooth way, but around this region, you have to go to the covering, and there it's the Ricci flow, and you keep this singularity here. So you've got a smooth solution to Ricci flow everywhere away from these points. Around these points, if you go to the covering, you can actually, you have a smooth solution to Ricci flow, so it's smooth in that sense, and you get past these singularities, so you can continue the flow. So that's the one of the applications. And so I should point out that so these first pictures of maybe a cone occurring like this in 4 dimensions, we now have I see there's a question. Yeah, please.
Do you know, so it may happen that's only infinitely many?
Yes. There's can only be finitely many, yeah. So I'm going to give a rough idea about why in a moment. Yeah, there can only be finitely many, and they're apart from each other. They're separated. Yeah. Okay. So this actually, we're looking at the setting that integral of scalar curvature to 2 plus alpha is bounded in dimension 4. So let's just stay with this for the moment, and then we see that these things may occur. This was initially, so I looked at this problem quite a few years earlier, and so did Bamler and Kui Zhang. They looked at this. Actually, their paper came out a few months before mine. They used slightly different methods. My method's more to do with these integral inequalities, which I showed, and they use slightly different methods, but there are some ingredients which are the same. The main difference is that I have this integral estimate, which is always true, and then I apply it to this setting. Yeah, okay, so we have these nice integral estimates which allow you to look at this, and we, both groups, myself and the other two, looked at this in the setting that the scalar curvature is bounded and showed that these sorts of singularities may occur, okay? So what this is all about is trying to understand what can happen in Ricci flow. So you may be looking at your solution, you may know something about the solution. Let's break the manifold up, or break the manifold up into regions where integral of the scalar curvature to the 2 plus sigma is bounded, then we can see what can happen there. Here I've done it on the whole manifold, but you can look at that. And then, of course, there are regions where that goes to infinity. You have to understand these regions. This is very complicated, but this is just giving you some idea about what possible singularities can happen. So an important thing about this is, you notice I like this little question mark here, because this region here, I told you it disappeared, and unlike the 3-dimensional case, the topology there is not understood up until now. So in the 3-dimensional case, you can always, just before the singularity, you can understand the topology, but in this case here, complicated. So this is, a few people are working on this. It's not quite clear what it looks like. So that will be important to understand in order to do something like reconstruct manifolds after surgery or after continuing the flow. You want to know what was the manifold just before you got to this part here, so you can say something. If you then continue on and continue on, each time you get a singularity, you do something, and you would like to understand what happened at each step. What was the topology of this thing, and what's the final topology that you have, right? So that's why that's an important thing to understand that's not understood at the moment. Okay, so yeah, that's the main ideas behind it. Here I've mentioned the previous work I just mentioned before. There are other integral estimates which I showed, which are valid for the scalar curvature situation, which are better suited to the bounded scalar curvature case. So these are sort of like weighted versions of these estimates. Don't really want to go into this in too much detail, just to say there was previous works in the setting of scalar curvature bounded, and I've mentioned Bamler and Zhang also looked at this. Okay, so I'm not going to go into all the details of this. So I'm going to flick through some slides quite quickly, because it's all just calculations. And maybe I'll just mention a few points that are interesting in it, how you actually get these integral estimates, and then maybe just 1 minute on how you get the orbifold solutions. So the equations of evolution of scalar curvature under Ricci flow are written down here. Of the norm of the Ricci squared, I've written them down here. And volume, I've written it down there. And with these 3 equations, you can look at the ddt of integral of this quantity here, whereby LVT is the quantity which I had at the beginning of the talk. So this is exactly the integral of f is the integral quantity we want to understand. So you look at ddt of it. And just using these equations here, you have to do some manipulations. It takes a fair amount of time, but you get this, evolution equation. And there's only, so I'm just going to mention each time one or two points which maybe are important and useful for the whole way of getting the estimates and the integral inequalities at the end. The first thing that may be interesting is this term here. So all the other terms are sort of lower order terms which are coming from the lower order terms, but this one here is involving the gradient of Ricci and the gradient of scalar curvature. And the most important thing is that it has a sign. So just go back quickly. You can imagine taking ddt of this Ricci squared divided by 2 plus r, for example, or 2v plus r, and you're going to get all these. If you write this as a Laplacian, so ddt of s equal to Laplacian, you're going to get all these error terms involving gradients. The nice thing here is that they all turn out to be so, if you put them all together in a nice way, you see that they have a sign. They can all be put into this, this norm here. This is the norm with respect to GT, by the way. So that, we just throw this one away then. And so all these mixed gradient terms disappear, which is really useful. And we get this really good term here, minus Ricci to the power of 4. I'll just go back a moment. Where does that one come from? That one comes from doing, r is at the bottom here, so when you do ddt of 1 on r, you're getting minus ddt of r, and you see here we're getting a minus 2 Ricci squared term times Ricci squared gives you the minus Ricci to the 4th. So you get a really good term there, and then you've got all these error terms you have to deal with. The only thing, so here you do a partial integration, assume the n's 0, so it's not important at the moment. You have integrals which you have to control, okay? And the one thing I'm just using Hölder and Young's inequality, you can get all these things under control using, and here's maybe the key feature, why I have to stay in 4 dimensions or Kähler. In the 4-dimensional setting, you use the Gauss-Bonnet formula of 4 dimensions, which tells you that integral of Riemann squared minus 4 Ricci squared plus scalar curvature squared is equal to 32 pi squared times the Euler characteristic, a topological quantity, so it doesn't matter how the metric's changing, plus some terms which are involving an integral on the boundary of n times by scalar times by sectional curvatures and second fundamental form, which I just call error, because for us it's under control. And here's the interesting thing: for the Kähler setting, there's a similar estimate. You can control this in any dimension for the Kähler Ricci flow. You can, using first and second Chern class, it's possible to equate this quantity here with the first times 0 quantity plus something that you've got under control. So that's one way that we deal with some difficult integrals coming up in the estimate, and that's the key feature to why we need to look at n is equal to 4 or Ricci, or Kähler, because we need to somehow get rid of this complicated term here involving the full curvature tensor. And the other estimates are just done using Young's and Hölder, and well, it's a bit complicated, but I'm not going to go into the details there because time's almost out. So what about the non-collapsing estimate? Well, Rugang Ye and Kui Chang showed a long time ago that you always have a Sobolev inequality, a sort of Sobolev inequality along the Ricci flow. You see the scalar curvature comes in, and you can combine this with some ideas of Caron to show, in fact, that if your integral of your scalar curvature to the power of 2 plus sigma is bounded, then in fact you're non-collapsing. And yeah, and the other estimate I already said comes from Bamler. Right, so maybe just a few words about convergence to an orbifold. So let's just stay, okay, I wrote here, let's just stay in the n is equal to 4 setting. This is what we've established. Now, how do you get this orbifold convergence? In fact, we saw a talk by Francesca a couple of days ago about harmonic maps and how you've got an energy there, and you have an energy bound, and you have maybe concentration of energy and nexts and so on. And in fact, this is the inspiration for how you get the orbifold convergence. So what you do is you take, you consider this to be your energy, Riem squared. It's bounded, it's a scale invariant quantity. And now what you do is you look at regions. So just as in, remember, she was looking like everyone does in the harmonic map, heat flow, or harmonic flow. They look at the energy as integral gradient u squared, and you look at regions where that's possibly concentrating or not concentrating. So you've got these, points which I call regular, and that means that integral of a ball, there exists some ball such that you're taking the evolving metric and you look around the point there and you look at the evolving Riem squared, and this is small. Just in the way you look in harmonic map heat flow and harmonic maps, you look at integral gradient gradient u squared being small. Here you look at these regions where this is small, where this is some very small constant, which can depend on all sorts of things. I don't want to go into the details, but it's just assume it's very small. It can actually depend on the solution itself also, so in a not too complicated way. In the end, it only depends on these sorts of constants that are involved here, but I don't want to go into all the details. It has to be small. And then you find out that if you restrict this, now you can take a fixed ball, fixed time, take time 0, and you take a very small s, and you look at the metric, the s is something way smaller than r, then this is smoothly, in the C infinity sense, going up to something which I'll just call LGT. Smooth. It's a smooth part of a manifold. So you get smooth convergence there. And the ideas are essentially, I think they're sort of inspired, well, no, they are completely inspired by the theory of harmonic map heat flow, that you try and then just prove better estimates for the pointwise curvature just using Sobolev inequalities and the fact that the energy is small there. And you can do that. And then you only have the irregular regions, so the singular regions is everything else. And there, that's a complicated region. You need to understand what's going on there. And you have to prove various estimates. And there, this part here becomes very important. Because what's happening is when you scale, you're always bounded by K0 once the integral of the energy is bounded. But I told you before, when you on a scaled level, this quantity goes to 0. So in some ways, it's like saying the Ricci curvature is going to 0 as you scale. And now with this extra information, you can actually prove further estimates, and you can show that the distance is not changing too much there with the help of the Ricci curvature bounds you get. It's a complicated procedure using the Nash, so methods of De Giorgi, Nash, Moser with this low integral bound. You can actually improve the estimates on the Ricci curvature, and that improves estimate on how the metric is changing, and you get control of distance around there. And then you see that actually using this nice quantity here, that everywhere the thing is still at a scaled level. Once you're scaling, it's still approaching something smoothly, except at the point where the energy is concentrating. And at that point, it's disappearing. It's just going down, and you can't say, at the moment, you can't say too much about it. But you can see that everywhere else that the solution is becoming, the solution is becoming almost smooth. And here's another important point. is that then when you take the limit, you get some sort of metric space, but here's something, it's the same in harmonic maps, is that that concentrated energy is now gone, right? The integral of it disappeared with maybe some bubbles or whatever, it's gone. So in fact, the limit space is now if you start rescaling it, you get to something which is flat, which has curvature equal to 0. Although it has a singularity, it has curvature equal to 0, 1 point singularity. And then you can see, using some arguments that have been used for Einstein manifolds, because you're on a Ricci flat sort of thing, you can see that if you you approach something, so the distance now of the Riemannian metric is approaching something which I just call x dx. It's a metric space. And now you start rescaling this. So you start taking rescalings of this x dx. So you start blowing it up. Let's just take I, with I goes to infinity. And you take a fixed point, one of these singular points. And as you do that, as I just said, the energy has already disappeared. There's no more concentration of energy. It's already concentrated into some bubble which is gone. And this turns out then to converge to something which is a flat Euclidean cone. So that shows you why you see these sort of cones in the limit. Because if you scale those things I showed at the beginning, you get a flat Euclidean cone, i.e. a Euclidean cone over S3 divided by gamma. And then finally, why do you only have finitely many of them? Because into a Riem squared is less than equal to k, so each time it's bigger than equal to epsilon 0, so you lose some, and there can only be so much. It could be a few of them are clustering in together, that's possible, which could lead to some sort of bubbling. But in the end, in the limit case, there can only be, they clustered into one point, the other ones didn't cluster, and you just have finitely many then. For each little bit of epsilon 0 of curvature here, you get at least one singularity, but you can't have too many. So yeah, so that's all I wanted to say. Thanks for your attention.
Thank you very much. Other questions?
Thank you for your very nice talk. I have a very general question. So in the last few years in mean curvature flow, a lot of has been done about generic flows. Does it make any sense to speak about something generic in the case of Ricci flow?
Okay, so I think so. I haven't, to be honest, done too much thinking about it, but I know that some people do think about it. I think it could make sense to consider it to avoid certain singularities, right? Certainly, I think it's possible that this could be a useful procedure. But since I haven't done too much research into it or read the results on it, I can't say too much about it at the moment. Yeah.
Okay, then I have a follow-up question. So in your case, you really need to use Chen-Gauss-Bonnet. Do you think it's a technical issue or something really is going to be very different in higher dimension?
Okay, so this is a really interesting and difficult question to ask. So in 4 dimensions, yeah, we use Gauss-Bonnet. For the Kähler case, you don't need it. You can use these other things. So one could hope that in any dimension you can get, maybe not this good, but some sort of estimates. Okay, so I've thought about this a bit, but I have come to no conclusion. Right? It's certainly something one should maybe think about. Can you get some sort of estimates in higher dimensions of this type using something else? So there are other versions of Gauss-Bonnet, but I've tried using those. They didn't lead to any success. The main problem there are other versions of relating curvatures which are called Gauss-Bonnet formula in higher dimensions. But I'm sure you're aware the problem there is that in the 4 dimensions you've got this very, very useful fact that the full curvature tensor can be related to the full Ricci and the scalar. And then the higher things, it's mixtures all over the place, and I haven't been able to have any success there. But it's still, maybe that's the wrong thing to use. Maybe there's some other way of getting some integral Riemann squared estimate or some other integral estimates of this type without using Gauss-Bonnet? I certainly think it's a very, very interesting question, but up until now, I don't know of any method that could lead to it. Yeah.
Perhaps a bit of a similar question. So, in order to see kind of conformal 2D bubbling in 4 dimensions, what I remember is that there are kind of these higher order curvature operators, Pennet's operators, which kind of lead to the same phenomenology. And now you seem to see the similar phenomenon in 4 dimensions, that suddenly point singularities and bubbling, you even use that language,
maybe
creep in. Yeah. And but all you say in justification looks completely algebraic, has to do with kind of the curvature tensor. So is there any kind of scaling or kind of more top-down argument which tells you that exactly in 4 dimensions you should expect these kind of point singularities to happen? Like in, for these curvature operators, it's clear, right? But is there a similar argument here?
Okay, so
it's the same question, I think.
Yeah, it's similar, but okay. At the moment, I'm not sure. Yeah, I should mention, by the way. So you said, you see bubbling, and I said, yeah, maybe, because I said it's feasible, and also that these singularities happen is feasible. So that's something missing at the moment, is an explicit example where the integral of the scalar curvature is bounded, and you see one. Nevertheless, after the scalar curvature being bounded papers, and this was the first time, people started thinking, oh, maybe there are these conical singularities in 4 dimensions. And then someone did show that these conical singularities can happen in some sort of way. So a guy called Appleton, I just remember there's another page on the slide, so it's not that important. Just go. Yeah, so Appleton, he showed that you can, starting off with a non-compact solution, he showed that, now here's the thing, I said it's almost like showing that these things happen. First of all, you don't have bounded scalar curvature for the thing that you're looking at, but he showed, so that's been tested. I don't think you have integral scalar curvature bounded either for these powers, but he showed nevertheless that you can take this solution, but then you have to take a sequence of times and you have to blow up, and then you can actually see a Euclidean cone, which is non-trivial. So you can't just let it flow and then say, at the end I scale and see the cone. You have to do this scaling, you have to choose them carefully, and then you see it. It's not exactly the same, but it's certainly, you see, the first papers showed, okay, maybe these things can happen. Now we see, okay, Appleton has created a situation where they do happen, sort of. And then in a recent paper of Bamler, he also showed in his trying to understand singularities, I think these are all inspired by these initial cone type papers, I think, at least this possibility of cones. He showed that you can always take some scaling around singularities and to see, and then there's a list of possibilities, and one of them is the cone. So you need to really consider it now. So it's even set up in the sort of analysis of possible singularities now. It's turning up. But to actually construct an example like I showed here that just really does go down to that, this still is missing. Yeah. And regarding the first part of the question, I don't know at the moment. This will be very interesting, but it's still lots of research going on to try and understand why they happen. Do they really happen in the way we show? So, yeah.
Any further question?
May I ask one?
Yes.
Andrea.
Andrea from...
Hi. So I have a couple of questions about orbital points.
Yes.
So did I get it right? So that to continue the flow,
yes.
So you get to an orbital point, you lift, and then you continue. Is that so?
Yes. Yes.
And but can you sort of project down the flow to the original manifold, or you continue just
maybe
on
you
the
want to
lift?
repeat the question? Because...
Okay, so Andrea was asking, oh, now I think it's very loud. So
Yes.
Andrea was asking, I'm being asked to repeat the question, Andrea, because I could hear it, but I don't think everyone heard it.
Mm-hmm.
Maybe you can say it now. I think we can hear you better now, maybe.
Yeah, whether, so to continue the flow, you need to lift the orbital points to a smooth manifold, and then you can continue.
Yeah.
I was asking whether you can sort of project down the flow, the continued flow to the original manifold, or you just continue on the lift.
Okay. Yeah, you can do both. So the point is that, of course, away from the singular point, everything's smooth, and then you can just use your lift that you got to see that, well, you can do the Ricci flow there. So the orbifold Ricci flow that you get, you can look at it on the manifold below also, but only away from the point.
But it will stay orbifold. Okay.
Yes, exactly. It stays an orbifold. Yeah.
The other question is whether you can get a bound on the group gamma, depending on the initial topology.
Sorry, whether you can get the bound on what?
On the cardinality of the group gamma for...
Yeah, okay. Not at the moment. So I think this, if I remember, okay, I'd have to really look once again into the argument. There are some parts there where there's some information about gamma and why it's only finite, of course, but it's okay. So I couldn't get many bounds on it. I couldn't really get too much control on it. Yeah, I can. Okay, I just am. I'm not sure. Yeah, that's a good question.
Okay.
Yeah. I'm really not sure about that.
Thanks.
Yeah.
May I ask another one?
Sure. Yeah.
Okay,
I say yes. What will you say?
Sure. You're not the chair. Okay. So your results apply when the manifold is either four-dimensional or Kähler.
Yes.
What if it is both?
Oh, okay. So, yeah. Okay. I don't think one gets any in. Okay. I haven't considered too much. I just thought, since we have both, I could use either the Gauss-Bonnet or the other one. I didn't really think too much about it. And in fact, the whole Kähler setting, of course, you have a lot more structure. And these estimates hold for higher dimensions also. And we want to look into what sort of singularities can happen there, but we haven't looked too much into that at the moment. So no, I haven't really. In that setting, I just said, okay, it's real, so we can see the orbifold convergence. Good question. I haven't really looked into that. Yeah.
Okay. Oh, just one comment about Felix's question, because I attended a course by Gilles Caron last week, and he sort of was explaining the similarity in terms of roughly W22 capacity somehow. So if you control Ricci squared, it's a bit like controlling the metric in W22 roughly.
Okay, yeah, okay. So maybe I can make a comment about that. That's a lot of control though, of course, right? Yeah.
Yeah.